a bunch of literally, optical tables have a bunch of, for example, beam splitters, okay, which are basically these little crystals that split light 50%, for example, right? Or they have, for example, mirrors, prisms, etc., which have these nice symbols that remind you of the Vector Institute symbol, okay? So from one way or the other, for example, in this holographic element, you actually change the angular momentum of light. In other ones, you gain a phase, right? Or you reflect the direction of the light, or again, create these superpositions of light, etc. So, and of course, the parametric down converters are the ones that generate entangled photons. Everything usually starts by lasers hitting a parametric down converter. The parametric down converter generates 2 entangled photons, and then you use them in your quantum optic experiment. We're going to be talking about experiments where we generate more than one pair. Okay, usually you take a laser pulse, you split it into 2 different. And of course, the basis will basically be the state of the photon and the path. Okay. So, how do you represent a quantum optics experiment? This is where we want to think about it. You can think about an experimentalist literally going to the optical table and, like Lego, starting to put elements. Oh, I'm going to put the beam splitter. Now I'm going to put a dove prism, and then I'm going to put a detector. Some of them probably make no sense, and that's the kind of thing we want to think about, right? But some of those experiments might do something cool. So this is where the connection to chemistry comes in. You can always write a graph as a sequence. And why is that? Because you can always think about a transversal of the graph, and therefore sequence representations of graphs are not unique, right? You can always imagine having 2 ways of transversing a graph with a sequence. But one of the things that my group has shown over the years is that string representations of molecules are actually super powerful. And we developed a string representation called selfies that is very widely used now for molecular design. Well, this is kind of the same thing. You can imagine building a string representation of your optical elements, and we're trying to show you here, it's how if you imagine having all these different moves in this space, you will be having a more and more complex quantum optics setup being built, okay? So that's the game. You have these elements and you put them together. And if you actually see the subsequent buildup of that quantum optics setup there, you can actually see from bottom to top how you start. You start with these 2 entangled photons that basically are now just generated, like pretty boring quantum state. But then now imagine that you apply some beam splitters, so therefore you have the superposition, right? And then the holographic guy adds these phases here, and then so on, so on, so on, so on, right? So the cool thing is that you can always write, say, a Python code or a Mathematica script that is very deterministic, right? Knows exactly what quantum operation to apply to the quantum state as you keep adding and adding optical elements, right? So you have a correspondence between the sequence and what will be the quantum state that is prepared by the quantum optical setup, right? So now, what we want to do here, and this is what got basically the Nobel Prize to Anton Selinger, is the idea of thinking the generation of highly entangled states, right? So, for example, this is a highly entangled state, right? So imagine that you have those 3 particles, and then if you measure one of the particles, you kind of determine what is the outcome of the other particles, and that's basically what people think. There are stronger correlations than classical correlations in this particular case, in this highly entangled state, okay? And you can always characterize it by what is called the Schmidt rank vector, okay, which will be basically the rank of all the partial density matrices of these photons, okay. But perhaps more importantly for us, that we want to have a continuous derivative of entanglement with respect to molecules. We want to have a continuous representation of entanglement, and the simplest possible representation. We all know it also has, basically inspiration also in thermodynamics. It's just the trace of the density matrix log density matrix, right? And therefore, that is the continuous measure of entanglement that we're going to be using here as a measure of how entangled is the quantum state that you generate. Okay, so I'm going to skip this. So, how do you build this variational autoencoder? Okay, we're going to actually have 2 different elements in the variational autoencoder. We're going to have a convolutional piece that actually uses this one-hot encoding to actually just build the state vector. And then we have a very simple sequential RNN type neural network that is going to be giving us back element by element. So it's very common that your encoder and your decoder are different in autoencoders, okay? So usually when we do encoders for molecules, we encode with some convolutional kind of encoder, and then we decode sequentially because we want to build molecules. We will build sequences of different lengths. So now, one of the things that you actually think about when you actually build these things is, how do I validate it? I would say for the first, and actually my students do it all the time, one of the first things you can do is say, okay, generate samples and look at them. So as a human, you can actually see if the circuits more or less make sense with your eyes. Hard to see here. For a trained chemist, when you see a molecule, you know if the autoencoder works, because more or less the molecule looks like the sample, and that's kind of in the eye of the beholder. Obviously, you can have more important metrics, but a good example will be if I randomly drew a setup from, you probably will not know necessarily which one is which. But now this is where the cool thing happens. These are setups that have zero entanglement entropy. You can actually see that the paths of the photons never interact with each other. This is kind of trivial, right? These photons just go out and you measure them right away. This photon just goes through that beam splitter, and this one just goes by itself. It's kind of a boring example. The photons never got entangled. Whereas in this one, you see it's a maze, right? The photons came out of the beam splitters and they went through all these elements. You see much more entanglement there. Every time they start interacting with each other, you build up entanglement, right? So you can see here, these more complex setups are building entanglement entropy of 5. This one 0. And what you can see here is the first test. For example, you can interpolate, which is really sexy, right? If I have this setup and I have this setup, are there equivalent setups in terms of how much entanglement I get? ISO entanglement setups that I can interpolate through and move in the latent space. So that's pretty sexy, right? Because you could imagine that maybe building, you want an entanglement of 5, but maybe building this will take you a month in the optical table, but maybe building this will take you a week. I'm not an experimentalist, so I don't know exactly which optical table is easier to put together, but maybe you don't even have an element in your hand. You might want to, So in other words, now we have a way of generating new quantum optic setups, right? So when we generate molecules with machine learning, we always like to think about uniqueness and novelty, okay? Novelty means, obviously, it's not in your training data. If you start generating only stuff from your training data, maybe the only thing that your model did is just memorize what happens in the training data. So that's novelty. And uniqueness is how many times do you get new setups? It has to do, obviously, with the size of your space, but usually these are good numbers, 0.99, 0.98, et cetera, means your model is working, okay? And then this is where we win over Mario's approach. Mario was sampling the space stochastically in his PRL paper, right? And he was getting about 50% of the setups were entangled and 50% of the setups were not entangled. Whereas in this case, we trained, this is a data set where we trained only on entangled, I forgot to say. We have two different data sets, one that has entangled and unentangled states. In this particular one with entangled states, we can generate 96% of entangled states. So we're screwing up about 4% of the time not generating entangled states, okay? So another important way if you can see if your model is good or not is you just match the distributions, right? So you want to generate the same distribution roughly as the training distribution, so that's a very good thing for when you do machine learning. And you can see here different states that have different, basically the subspaces of different excitations, right? So this is an example of one that has 3 excitations or 4 excitations versus 0 excitations, right? Or flips of the photons. And that gives you an idea, okay, my distribution is actually good, okay? So more examples of interpolations. I don't know why I'm showing you another interpolation here. I forget. This is a talk I don't give very often, so I forget what the story is here. Whatever. I think we're interpolating, for example, again, above very, very low entangled setups, and here there are very, very high entangled setups, okay? And somewhere in the middle, we have intermediately entangled setups. So now, I want to keep this workshop in time, and I know I have 5 minutes left. So even though I started late, I'm going to compress my talk. Matthew, your second part of my talk will disappear, okay? So Matthew and I have a paper, I'll show you on one slide about it, for example. But, okay, so what is cool about this, okay? Like now, what did we learn, okay? So I just showed you, okay, I'll tell you my philosophy about machine learning here, right? Obviously, for machine learning in science, you want to learn something from what you did. It's just super cool to show you that I can interpolate setups. or maybe a good engineering thing is that I can generate setups that are easier to make experimentally. But maybe it's more important to think about what is the science behind it. What are you learning from it, right? And one of the interesting things that we want to keep exploring with Alba Cervera, Mario, and Daniel is when you actually do these two-dimensional representations of the latent space, and you actually want to look at which states are entangled and which ones are not. I'm going to put my mouse here. You see here in the entanglement, you see that there are some overlapping regions in the latent space, right? That are perhaps the ones where the science will be more interesting. What is the setup that just by changing one element just completely disentangles itself or not? Or is in the border between entanglement and not entanglement? Those are things that, for example, could be interesting for us to explore. And perhaps optimizing to be in that particular region is pretty sexy, right? Finally, I haven't told you about optimization. Well, this is an example of how far we can go if we actually do the same thing I told you before. I follow the gradients, which was our dream, right? Follow the gradients and generate a maximum entangled state. This is going to be very interesting because imagine that now, instead of giving you four photons now, I give you 20 photons. 20 photons you can start simulating in a computer still. Probably you can go up to 40 photons or something in a supercomputer, about then, maybe 50, who knows, exactly the number. There is not so obvious that you're going to be able to find out what is the best setup, right? So there, following a gradient is very important, the same way you follow a gradient in machine learning to find non-obvious things. And this is where things get very sexy, right? If we follow the gradient and optimize to try to generate very entangled states, we get to entanglement entropies of about 10. Whereas if you generate random states from Melvin, the random sampler with the same effort, the same number of samples, can't get that far. I think this is the best, actually, probably many more samples actually Mario kept running, and he was never able to find this very weird state that have such a high entanglement. So sampling is not as effective as following a gradient uphill, and you can see here an example of numerical experiments that show you can get to way higher entangled states by just following the gradient, right? So I think that's an example of why you want to do this type of experiments, okay? So I'm going to end with the conclusions for this part. Unfortunately, the second part of my talk will not be presented, but can we experimentally implement a computer dream quantum optics experiment that comes out from this? I think that will be the dream. More and more people like Dirk Eglund at MIT and others have reconfigurable quantum optics chips that you can actually reconfigure on the fly. So you can just imagine an experiment where you actually reconfigure a quantum optics experiment in a chip by using machine learning and on the fly generate maximum entanglement. So that would be like another potential cool paper for Nature Quantum and Machine Intelligence if you actually show that you're generating highly entangled states. So what I was doing with Matthew, here are the people that did this work, Tony, Shomei, Mario, and Daniel. I don't even know if Daniel is connected, but if Daniel is connected, he can also help answer a lot of questions. But I know Matthew is here, which also worked with me and Tija and Daniel in the to represent the quantum dynamics. So I'm going to flash you the presentation of Matthew, but what we did there was really cool, is learn with a neural ordinary differential equation the motion of a qubit as it decoheres, which I find is super sexy, that a neural network can learn implicitly what is the behavior of the Schrodinger equation, right? So dreams for that from Matthew's project was, can I have a neural network learn how to factor a number with Shor's algorithm or something like that? Okay? And on that note, I want to thank my research group. And then I don't know if I have time for questions. I think there is some time for questions, right? So I'm going to just stop here. Thank you. So if you ask questions, introduce yourself, and then yeah, so people know. Okay, Professor Ismailov.
Yeah, I'm Arthur Ismailov.
Arthur,
yeah.
Use the mic.
Hi, I'm Arthur Ismailov from Chemistry Department, UFT. So my question is related to entanglement. So we generally presume that having more entanglement is good. Could you elaborate a little bit why is that? And also this question is motivated by my understanding is that entanglement is somewhat basis dependent, right? So it may not be like the case that all entanglement is great, and maybe there are other quantities besides the entanglement that you want to optimize. So if you could elaborate on that.
For generating entanglement with quantum optical states, there's a fundamental physics thing going on. There is actually, I have a paper with Alba Rivera and Mario also, where we use superconducting qubits to build like a doubly excited state, entangled state in a superconductor, which was very exotic. Sometimes people want to build very exotic quantum states, right? For example, in that case, was using a Q-trip state of a qubit and showing that you can entangle Q-trips. So some people just want to show, look, I entangled this bit, right? So that's number one. And that's a big field, and that's what Anton Stellinger likes to do. Another field is say, what can I do with entanglement? So in quantum optics, which is perhaps the best example here, what our friends at PsiQuantum are doing is they're trying to generate entangled states at hundreds or hundreds of thousands of photons. And those states have to be controlled to be what they are trying to do. As far as I know, they're trying to create something called a cluster state, which is a state where you can actually, by using measurements, carry out a quantum circuit. Okay, so what they're doing is they're entangling a bunch of photons, do measurements on those photons to implement gates. But the interesting thing is that at the end of the circuit, they keep entangling more photons. So it's almost like a rolling tape, where you're entangling photons on one side, measuring on the other, and actually carrying out a quantum circuit. That's what I understand is, for example, the model of quantum computation with optics that people like PsiQuantum want to do. So one example is build a lot of entanglement, measure it out, and then compute as you're doing that. That is called one-way quantum computation. Of course, and the other thing that you also know very well, of course, yes, of course, entanglement is basis independent. Let's assume we're just using, say, a qubit computational basis, not to simplify things. But finally, you probably also, for everybody here, people want to know that usually highly entangled states in your computational basis, say, are harder to represent in a classical computer. So for us that are trying to do quantum simulation, for example, the research of Juan or the research of Anatole, your research for myself, what we want to do is build entanglement in our models, right? Because that's going to be harder to simulate classically. So that's the reason why entanglement is important. And of course, yes, there's many measures for entanglement. There's basis dependence for it. It's not clear sometimes if something entangled is better. Many, many questions, and that's why there are workshops on quantum entanglement themselves, right? Any other questions? Introduce yourself, please, so we know who you are. Yeah.
Hi, I'm Matt. I'm in Juan's group. I'm just wondering, when you're doing this optimization, maybe to maximize entanglement or something, could you add in penalties of like how hard these experiments are to do?
We did not add penalties of how these experiments are, but we could. Your question is very good. We could say, I only have 2 beam splitters. You could condition the optimization in, I only have 2 beam splitters in the lab, or I don't really want to use this quantum optical element, or another measure of hardness that you could imagine building. At the moment, we just assume you have all the sets of elements and that all the elements are equally hard to implement. But obviously, the magic of machine learning is you could have a penalty term that guides the optimizer to try to, say, minimize that cost, for example, right? At the same time, it maximizes entanglement. So that's like a very good extension of this. Thank you for the suggestion. But we didn't implement it.
There's no more questions, then can we thank Mr. again? Next up, we have Professor Nathan Wiebe.
Matthew, should I disconnect your laptop, or what do we do with? I'll let you deal with that. Let me just in the meantime mic this guy. Professor Wiebe, mic.
All right. Cool. Thank you. All right. Maybe this one? Okay, yeah, I'll give this talk. Yeah, that's the nice thing about being so disorganized. I didn't put an abstract in. I get to decide at the last minute. But thank you.
Well, actually, interestingly enough, I'm going to be talking about that fact. So thank you very much, everybody, for coming. And now this is actually not the display you want to see. Let's duplicate slideshow. Come on. I know you can do it. Oh, yeah. All right, cool. So thank you very much, everybody, for coming. So today, what I'm going to be talking about is generative quantum machine learning. And in particular, this is something that I feel has been neglected for far too long inside the field of quantum machine learning, in part because of the fact that so much emphasis until recently in the classical community was largely in discriminative tasks. I mean, this is largely because of the fact that if you're looking at, say, classification, you know, you can always get good numbers, and bigger numbers is more better. So for a long time, I think there was this attitude in the community that generative tasks were of less interest because of the fact that you can't race as effectively against competitors. Of course, the situation in the classical world changed radically within the last year because of ChatGPT and things like that coming out. But nonetheless, I'd like to argue that in the domain of quantum, generative learning is arguably more important than discriminative learning. So I'm going to be talking about that. I'll show you a new approach that we've developed in order to be able to do this that addresses some of these issues of gradient decay that existing models often end up facing. And further, I'm going to be showing a new approach that will allow you to come up with a method for generating approximate ground states for molecules just by specifying a nuclear coordinates. So the idea is to build a quantum ML agent that's capable of solving a useful task, i.e. preparing an unknown ground state of a molecule given some training states that are the ground states of that molecule and other configurations. So that's my talk. So you can check your email now. But okay, we all know about this. But basically, high level, how do we normally end up thinking about generative models? Some of the simplest generative and earliest generative models that we were seeing were, of course, the autoencoder. The idea behind this is actually frequently used in deep learning supersampling, which for those non-gamers out there is a fancy technology that NVIDIA is all pushing on its video cards these days that allows lower resolution images to be rendered and then upscale to effectively high resolution images. And the way that it ends up working is through a neural network that ends up taking this kind of a form. It starts with a low resolution image, which then gets decoded into a low dimensional latent space that then gets expanded out to a much higher dimensional image than the one that came into it. And by training these models on large corpuses of images coming in, actually the performance is pretty good. And, you know, in practice, you can end up getting, for deep learning supersampling, much, much higher frame rates at very little noticeable image degradation. So these are some examples of generative tasks that we're taking a look at. And for something like this, it is kind of nice to think of because we can actually figure out what the notion of a loss function would be. For example, we could envision a situation where what we have is we've got like some image, and this is clearly the Mona Lisa over here. All right, there, see her hands are kind of crossed in the middle? Yeah, totally. Now, I'm sure if you threw that into Midjourney, you would definitely end up getting a Mona Lisa back out. But in any case, the idea is by comparing the output image at a particular resolution to the input one, you can end up generating a loss function and train with respect to that loss function. So this is one of the things that is nice about some of these tasks. If you have some gold standard images that you'd like to be able to see come out of it, you can basically measure the fidelity between the two of them. So the question is, like, how are we thinking about machine learning in a quantum world? There's two sorts of tasks that that one could be interested in general in quantum machine learning. The first is this case where we have classical data coming in. So imagine what we wanted to do is we wanted to recognize handwritten digits using our quantum computer. So what we would do is we would like to be able to encode those vectors of handwritten digits as vectors inside our quantum computer. Now, there's two ways we could do this. We could represent them as quantum bit strings, or we could represent them as quantum state vectors. So for the sake of simplicity, let's just assume that they're representative quantum state vectors. So we begin then by encoding those as some state. The second approach, which I think is more interesting, is the case where we're actually trying to learn directly off of quantum data itself. Okay, in which case, this data could be something that comes from a quantum subroutine, like a quantum simulation. And, this could represent, for example, the ground state of a molecule, which, of course, ends up looking like this. Again, Alán's art is far better than mine. Then what we do is we want to build a quantum neural network. And a quantum neural network in this context is just a parameterized unitary. So we've got a unitary matrix that is a function of a bunch of different parameters, and that will transform our initial state into some final state. And then what we'd like to do is we'd like to be able to measure something coming out the other side and optimize the value of that loss function corresponding to that observable, okay? So this is basically all of QML in a nutshell. For those of you who haven't done much QML, this is actually also identical to variational quantum algorithms. It's just the same shit, different flavor. To take a look at what a quantum neural network actually ends up looking like, these days, actually, we don't quite have the same nice, slick mental models for what a quantum neural network actually is. In fact, there's many analogs of a quantum neural network that could be considered. The most popular version that people end up considering is this parameterized quantum circuit, where you consider a whole bunch of these gates over here, G, each of which is individually parameterized. For example, you could envision it being an arbitrary single qubit unitary, like we have over here. And then we have some type of a circuit that builds entanglement coupled by in-between layers of individual basis transformations for the individual qubits. So this is probably the most popular way of building the analog of a quantum neural network. And as the depth of the circuit goes to infinity, we can actually end up implementing any arbitrary quantum transformation. And so that's the basic idea. We do all of this, and we usually measure just one qubit at the top. Or if we're looking at a generative task, maybe we want all of this coming out the other side. But the big advantage of quantum machine learning that everybody's really excited about is the dimension of the space. So n quantum bits allows us to represent 2 to the n dimensional vectors. Okay? That kicks ass, right? So we have the ability to have represent immense vectors on our quantum computer. But unfortunately, this comes with a major cost. And the major cost is it's really easy for you to end up getting lost in these high dimensional vector spaces, because we have to optimize our functions over these spaces. And also, the other thing is that we only can learn information a couple of bits at the time. So while we have 2 to the n dimensional vectors, every measurement of this will end up giving us at most n bits of information. So what that ends up meaning is if you want to resolve a really tiny gradient, you can only resolve those small gradients using many measurements, because of the fact that these systems or quantum computers don't allow us to be able to extract information out as effectively as classical computers do. So the basic thing that we want to do is we'd like to be able to really determine how bad this whole thing is. And it turns out, actually, what we can do is we can end up using arguments pioneered by Jared McLean initially, that on average, the expectation value that we end up seeing for these types of models that I ended up describing previously, and a linear objective function, like I described at the top, will yield exponentially small values of the objective function, which is bad. And worse yet, the gradients are exponentially small, so you can't even train. And furthermore, to make it even worse, in order to resolve those gradients, you need provably exponentially many measurements of the state. So you're just totally hosed, all right? And this effect is called a barren plateau. And basically, what ends up happening is that you end up, visually speaking, run into the situation where almost all randomly generated states end up being concentrated about a narrow band around one of the equators of the unit sphere. And this concentration that we end up seeing is basically what ends up guaranteeing that this will create problems for almost all randomly chosen neural networks. So first question is, can hidden units generically help? Well, this is one of the great hopes that we ended up having. And the idea basically is, imagine that you've got a deep model, something that ends up looking like this, where we've got some latent space at the top, and we've got some visible space down at the bottom. And what we have is we have all of these quantum couplings. These represent places where 2-qubit gates could be carried out. So it turns out that if these two systems become highly entangled, then what that ends up meaning is that quantum information can't be thought of as being localized in either of those two subspaces. Instead, the information gets spread through the entire system. So if we follow the same sort of pattern that everybody follows in ordinary machine learning, and they say, okay, well, I'll just put some randomized gates in here, I'll get a huge amount of entanglement. Entanglement's a good thing, right? Well, then when we throw away all those hidden units, in this case, most of the information is non-locally stored over the entire network if you've got entanglement. So throwing away the hidden units actually throws away most of your information. So this actually ends up showing that entanglement is harmful, believe it or not, for quantum machine learning, not helpful. And furthermore, that following the standard deep learning paradigms that we know and love will actually end in epic failure. And you can end up showing that, similar to the barren plateau result, that this will lead to exponentially small gradients. So how can we get around this? Well, one of the ways that we propose getting around this problem is by switching to generative tasks. The idea basically behind it is to, instead of trying to, even if you wanted to solve a discriminative task, we propose pre-training using a generative objective function before we start with that. So the idea basically behind this is very similar to what's done in Boltzmann machine training. In Boltzmann machine training, they suffered from problems with vanishing gradients, and a ton of samples were needed in order to be able to determine the small gradients that end up showing up. And one of the reasons why, admittedly, it didn't have as much legs as we see with the other stuff, but one of the things that helped it get along was the fact that they were able to train with respect to the KL divergence. So the question is, can we train with a quantum analog of the KL divergence? It turns out the KL divergence, the quantum analog of it, known as the relative entropy, has a little bit of a pain in the ass to it. It turns out it involves a matrix logarithm. And differentiating matrix logarithms blows because of the fact that matrix logarithms don't obey the chain rule. So the derivative expression for it is really awful to deal with. So in practice, a better approach for dealing with this is to work with what are known as the Rayleigh divergences. The Rayleigh divergences are, can be used in order to find upper bounds on the KL divergence. For example, alpha equals 2 is a upper bound on the quantum KL divergence. And it fortunately ends up taking the form of an ordinary logarithm, not a matrix logarithm. So that guy can just be differentiated using the same rules you know and love. All right, so then that's what we do. And basically what in our paper, we show that we can train with respect to this objective function in polynomial time, provided that the trace of rho squared sigma inverse is bounded away from 0. Now, rho, for example, rho could be equal to the training data represented as a quantum state, and sigma is equal to the generated. Wow, okay, I need more megahertz in this machine. The fact that it's measured in megahertz is probably the problem. But in any case, that's basically this. It turns out, of course, you can switch the two because with divergences, it doesn't really matter the direction. It's really nice to use sigma as a generated case because generically it won't have a kernel when we generate it, but your training data might have gaps in it. And so sigma inverse might not be defined if you take sigma to be your training density matrix. So that's the idea. So now let's take a look at a particular problem. One of the challenges facing quantum machine learning is that often we don't really have a killer application, to be honest, because honestly, most of the classical tasks, there isn't an exponential advantage. So what I would like to do is my collaborators and I did, is we wanted to find an example of a well-motivated quantum problem that quantum machine learning might be well suited for. And here's the problem. The problem basically is what we have is we've got a bunch of electrons, which are all orange for record, and nuclei, which are also blue. And the idea basically behind this is that what you want to do is you want to ask the following question. Can we learn a model that will take the positions as an input vector, like imagine we have x1, x2, fed into your system, corresponding to, say, these two nuclei in some configuration. What we'd like to do is we'd like to generate the ground state for this, not the ground state energy. We literally want to program the quantum computer in order to find the ground state. So the idea basically is we construct a sequence of pairs. We have x1, x2, and then we're going to have row 1. This is the quantum state, that's the ground state at that configuration. Then we might have, x3, x4, row 2, and so on and so forth. So our training set then corresponds to all of these different configurations and some ground states. And what we'd like to be able to do is we'd like to be able to train a network to be able to deal with this. And the way that our network ends up going is we first build a ordinary neural network over here that will take in these vectors of positions, and then they'll output a representation of theta up here. Now, theta, if you recall, theta was the parameters for these rotations in the quantum circuit over here. So basically, the idea is it guesses the variational parameters that would approximate the ground state. And then what we do with this is we go through and we train with respect to this objective function. We minimize it and follow the gradients in order to minimize the loss over our training set, and then evaluate how well it ends up working on molecules that it hasn't seen. And so here are some examples. We've got many more in our paper, but I just wanted to give you a hint about what's going on here. So the picture on the left is the energy as a function of the separation of the hydrogens being stretched apart along this direction for H2O. And the circles over here, these are the points it's trained at. So we provided it the wave functions only at those points, and we've taken a look at how it predicts the energy and the ground state at different configurations. It was trained in order to maximize this, but it wasn't trained in order to maximize the energy. That's why I did both of them. And so you'll note that the energy actually it does a really, really good job. It starts breaking down a little bit as you go to disassociation, but in the middle, it's actually doing a fantastic job, much better than we thought, with only 5 training points coming in. So this shows that generative training can work really, really well, and we tested it basically on hydrogen chains and larger examples. All the ones that we looked at. One of the things that I should mention are our fundamental limitations. One of the fundamental limitations that we very often at quantum. And one of the reasons why we can't improve in our paper that if we were able to build on learning data sets, take examples from one side of the ground state on the other side, we actually use this in our development. Turns out there's a Hamiltonian after the deadline, in fact, such that the ground state problem is solving research. Rubber search is an example of a problem that's going upward and lower down in the variables. And so we show that if we find that with like what over the square root half, then we would be able to use such a protocol in order to be able to solve problems. What this ends up meaning is that all our data work, these
we applied the exact same methodology in order to build thermal states. The cool about this problem is because of the fact that the objective function both where sigma is and sigma inverse is just a change. So even the age really build that either theory and optimize. That allowed us to go through, and you see that very well. No apparent evidence of apparent plateaus, and the result actually is better. So modern machine learning is still in its first understanding that's the question. Quite frankly, I think at the moment, more time and effort should be spent after quantum machine learning. And furthermore, under what circumstances, we end up finding that generative really has an advantage of the fact that some of that is very plateau. And we showed this by showing ground state, thermal state, and so my hope is that we that perfect study will be able to come up with better examples of formal learning problems that genuinely could be promising. And furthermore, my hope is that by understanding studying this, finally be able to figure out.
Are there any questions?
Hi, I'm Anatole von Lilienfeld. Thank you so much. It was really interesting. I especially like the application in the end, of course. So I was just wondering if you have the right wave function, then your energy must be fine, right? Correct. So I was wondering, you showed this fidelity. Was that the overlap of the true reference wave function with what you predicted, or?
Exactly correct.
Okay.
And we expected the two were correlated, but it was because you're optimizing one, it doesn't necessarily imply that the best model you going to necessarily be the best one. Okay, so
right.
Yeah.
And are you exploiting the variation in principle in your wave function, or you're simply, it's pure interference?
Optimizing for fidelity.
Right. Okay.
And specifically using this radiation divergence.
Would it be possible to combine it with like an iterative solver for the variation in principle? I mean, you should be able to use because at the end you have a neural net, right? And you should be able to use that like a basis set expansion of your wave function, right?
It's really just a question of what the effective function. We want to stay away from the energy is one of those quantities that certainly has very plateau, whereas our objective function doesn't. That's why we stay away from it, but we obviously could include variational information as well in so you can consider alternating where you create steps with respect to one objective versus the other one. A bunch of things I'm not sure Professor.
Yeah, I think that's really beautiful because in some sense you'd be doing what the measurement does, no?
Yeah.
When you actually collapse the wave function towards the observed state. But then maybe a second question, when you look at the phase transition you described, could you go back to that and figure that there were these, So we just posted a paper on Chem Archive where we found that if you diabotize those states, so the left-hand red one continues as the right-hand blue one, right? And then vice versa for the other. Then everything becomes smooth and you avoided the problem, right? And I'm wondering Could that help in your case as well?
If you're able to compare the exact verse exact. Adiabatic algorithm for blue trees. It's precisely the effect that you're talking. But here we run into a bit of a problem trying to do this for search because of the fact that it turns out that we can try to jump the tracks going down like that. Pretty effectively, there's something that goes wrong with it.
But in principle, your method is applicable to any state, right? I mean, why you've mentioned ground state in the beginning, but is there a reason for that other than?
The reason why it's ground for fidelity. We don't care about ground state. I just use ground state because.
Can you guys hear me? Yeah, good. Thanks a lot for a great talk. I'm Andrew in Juan's group, PhD student. I just wanted to see if I understood correctly. I mean, for the preparation of the ground states, you are ultimately, the idea is to determine those the variational parameters of the gates to optimize the fidelity, right? So I didn't fully understand when you extend that to thermal states and mixed states. Like, how does that approach extend to mixed states? Like, I didn't fully understand that.
Singular if you don't plug it in right.
Okay.
I don't know the class.
No, I have to hold it up for you.
Okay.
Thank you. Okay, we hardly possibly get right, and we do our
And then we have other people with a longer hydrogen.
But
Or make sure that it needs for a random initial.
yeah, but my point is that
How we find the answer. That we provided the one state. We have to go.
Is this one so big?
Yeah. We'll be able to.
okay. They somewhere
so it takes 7 parts.
That's like key places stuff, correct?
I don't think so.
Bring it back to the original one, because if you just plug it in, it should be.
Okay. I just want a mirror, so like I can see the slides here, but maybe it's better. Yeah, that's it. Okay, I think it's it. Yeah.
Mirror or extend
To show first.
Oh, that's easy.
Yeah. Sure.
So, show your desktop.
Okay. There should be another display. With my browser. Okay. What's this one?
I have a question for you. Instead of doing the physical, why don't you just go on Zoom and share your screen on Zoom?
Oh, I have like 3 displays here. I see. Yeah, I can try doing this. I think if okay, this is arrangement. If I just remove one of them, it will help somehow. Maybe. Oh, yeah. If I put this and no, I cannot disconnect it. Okay, I'll do it through Zoom.
Yeah.
Yeah.
Basically, the change of like the coordinate, you define the coordinate, you go to reduction of the gap,
I don't think I can share on Zoom. Yeah, I'm not allowed because I'm not an organizer. Yeah, no worries. It's fine. I'm surprised it didn't take.
if you're a speaker, you need the break, like you said, there will be a new strategy. Not his fault, but generally, for a speaker, session.
Well, I think I almost figured it out. Well, everyone, my name is Kirill. Yeah. Sorry for this thing. I'll tell you about Wasserstein quantum Monte Carlo. This is a joint work with like, many people, not all of them from Vector. I just forgot to put their affiliations. Yanis is from EPFL. Chung is from Austin Technical University. Max is from the University of Amsterdam. So first, I want to quickly recap like quantum variational Monte Carlo, even though you all know this approach, just to be on the same page. And then I want to kind of go one abstraction higher and consider minimization of energy on non-parametric manifolds of all the possible distributions as just like a gradient descent. Then we will consider how to project them back on the parametric manifolds, and we'll see that like it gives us like different algorithms and probably like some degrees of freedom. And finally, we will discuss why incorporating some like notions of Wasserstein metric and optimal transfer can improve our results. So just to start with the like, stationary Schrödinger equation we want to solve, we're given the potential and we want to find the wave function and the energy, right? So this is like super usual setting, and to do so, we want to minimize the energy. And here, like throughout the talk, I will operate in terms of density. So because I think this work is mostly like by ML folks rather than quantum physicists. So the density here is just the absolute squared value of the wave function, and energy just depends on our density, let's say. But throughout the talk, I don't want to talk about the wave function, but I assume it's like anti-symmetric, and we actually parameterize it in practice, and so on and so forth. So energy is some expectation over our samples of some local energy function, which looks like this, but it doesn't really matter how it looks like. So what really matters is that to estimate the energy, we need both to collect the samples from this density and the model of the density itself. So one iteration of quantum variational Monte Carlo looks as follows. We have the density model with some parameters theta, and let's say it's like a neural network that just spits out the density. And we sample, let's say, using CMC from this density. And then finally, having the density and the samples, we want to estimate the gradient of the energy with respect to the parameters of our model. And this also doesn't matter right now. And then we just do like a gradient descent, right? We just take this gradient, we can estimate it using density and samples, and then we just update our parameters using the negative gradient. And we know that, once again, like to estimate the energy, we need both the density and the samples. So we have to collect new samples from the updated density, right? Otherwise, there will be like a mismatch. So this is quantum variational Monte Carlo, but let's now go kind of like one level higher in abstraction, and let's consider energy minimization on a like non-parametric family of distributions. It's just like, so far we can say all the possible distributions in our continuous state space. So energy defines a function that maps any distribution to a real number, to a scalar, right? So it's kind of natural to write things down like informally that let's take the gradient with respect to distributions, let's say there is like such a technique, and then update the whole distributions here. And we assume we have like all the computations. We just operate theoretically, we have like infinite compute, so we don't care about density samples, we can get anything just theoretically, what will happen. Formally, we can formalize it as just like proximal gradients. Proximal gradients is quite easy. That's, we have the current density QT, we want to find kind of the infimum of the energy with respect to qt plus dt, but also we want our step be local. So, I mean, if we don't have this scale here, we will just find the global optimum of the energy, and like there is no value in this equation. Then, so we want to stay close to our previous step. We want to do like a local loop. That's why we put this scale, and we want to minimize the energy. And this thing can define the gradient, like step of a gradient descent for us on the space of distributions. But we want to take the limit dt to 0, and what we'll see the following PD. So this will be our gradient flow. So the density will continuously change according to this PD, minimizing the energy. And once again, this equation doesn't yet bring us any intuition. So let's just say it's like something. It's dq dt defines the evolution of the density in time, and this is like a very intuitive physical process in that sense that like we encounter it all the time, right? In nature, that like some density. Well, somehow here ut is the orange density, so it's kind of like our model, and target is the blue density, and it's not the quantum energy, but let's say that our energy is lower when we are closer to the target. So the target is kind of a ground state, and we want to fit our model there. And this is what this PD tells us. This is what's going to happen, okay? So if we have all the compute in the world, we will just slowly, perfectly fit our model into the target. Now I want to make a step back and just play around with this equation. This is what we had before, and we put the KL here. What if we put Wasserstein distance here? We'll get another notion of closeness in terms of distribution, right, based on the optimal transfers, which defines distance, so on and so forth. But just another thing we put, and once again, we take the limits, and we get another PD. And we'll compare these PDs a bit later. So far, let's first take the picture. We just get another something on the right side, like just different evolution of the density. Model targets, that's what we start with, and that's how it runs. So you see the behavior here is different, and that's kind of funny. We now have like different dynamics on this like space of distributions going to the targets. So maybe we can use it somehow later. So what we did so far, we just defined two different gradient flows on the space of distributions. Once again, it's like non-parametric, only theoretical. And these are their definitions, just different notion of closeness in terms of distributions. These are corresponding PDEs that we can derive easily from the first line. And this PDE, it actually reweights density by teleporting mass. So this guy here is this kind of like reweighting term. So you can imagine this to be as follows. You sample from your density, you assign the weight to all of your samples, and then this PD tells you the following. You don't move any samples, you just reweight them, okay? You just change the space. So in some sense, you don't kind of explore the space. So here you can see it's right there in the end of the gear. So the Gaussian starts moving to the right, but then it starts teleporting mass. So it assumes like there are like samples all over the space. It just reassigns weights to it, right? So the right-hand side PDE, that's a very different thing. Instead of reweighting samples, it pushes them around according to this vector field, because the right-hand side is essentially the continuity equation, okay? And that's why instead of teleporting mass, it actually splits the Gaussians in two and then assigns each Gaussian to each of the target modes. So far so good, but how do we use it in practice? And in practice, we want to project every step. So let's say we at some point we have parameterized our current density with these parameters, this black dot here, right? And after it, we do like Euler scheme one step. So being here, we use our PDs and we just make a step along this red line, along this red arrow. So the bad news is that we go off our parametric manifolds. The good news is that we can project back. So we take this density and then we basically find the closest density in terms of ETL in the parametric manifolds. So you see two dynamics here. One is according to one PD, another is according to another PD, and they have their corresponding projections on these parametric manifolds. So now we can change a bit quantum variation of Monte Carlo. So let's say we follow this Fisher-Rao gradient flow, which corresponds to KL. It's not really KL, but the same local behavior, blah, blah. It doesn't really matter. It's like the thing that teleports mass, okay? We have the density, we have the samples, as in quantum variation of Monte Carlo. Then we assume that our current density is our parametric model. And we do one step of the Euler scheme predicting this guy. Like, we can estimate it point-wise. Then we say, okay, now let's define the following loss. This is KL between QT plus DT and our parametric model Q theta. And we update our parameters according to these laws. So then we, of course, need to propagate samples further, right? Because we updated the parameters. So it might look different, but this is actually what quantum variation Monte Carlo does. So this is just like putting these two lines together will yield you the quantum variation Monte Carlo algorithm. So now, since we consider like different gradient flows on this Wasserstein manifold, we can like manifold of distributions. We can put another gradient flow here, and this will be two Wasserstein gradient flow. And once again, here I just write down in the same like theoretical terms that we do Euler scheme, then we put in KL, then we take the gradient. Actually, it will just result in just a different loss for your neural network that you implement in several levels. And let's see what happens in practice if we just implement it. We just try and do it. So these are for different systems. This is energy, and blue line is the quantum variation Monte Carlo. Orange and green lines are our algorithms. And here, like, it's a bit better. But we know that, like, the prediction of energy is not enough to get the right ground state. So we can take a look at the variance of the energy because the local energy should be constant, right? And here we see, like a nice improvement up to 10 times, I think, for the same amount of iterations. And we can also, since we operate kind of with these gradients of the local energy, we can also look at the norm of the gradient of the local energy because the local energy in the end has to be constant. So the norm of the gradient has to be 0, and we can also see how does it vanish here. So like we get better results, but that's not like the main point. We would like to understand why does it happen so. And our intuition so far is that this thing teleports mass, and this thing transports mass. So right here on the pictures, right? If we would have only densities, it doesn't really matter because like our neural network can probably learn this and that. But what's crucial is that we also have the CMC step, which usually is done by propagating samples further. And if you look at this GIF, you'll see that once we start teleporting math to the right mode, it will take a very long time for MCMC chain to converge. I mean, of course, like theoretically it will converge and so on and so forth, but in practice we run like a very short MCMC. We would like to run a short MCMC to save compute. And this is our current intuition why this works. So we'll put it on our Python. So actually this Fisher-Rao gradient flow is nothing else but imaginary time Schrödinger equation evolution, just written in terms of densities. And that's it. Then we can mess up with the gradients a bit. We can consider Wasserstein distance, but with a different cost on the like tangent space, and put like C any convex function, and it really helps in practice. And these plots are for these different costs actually. We can interpolate between them, considering Wasserstein Fisher-Rao metric on the space of distributions. And you'll find all the derivations of the gradient flows if you're wondering codes and exponent details. That's it. Yep.
So Nathan Wiebe, the University of Toronto. Quick question.
Have you considered whether or not you could apply these ideas for approximate Bayesian inference? Because it seems like actually the same sorts of problems end up showing up, you know, with like expectation maximization when you try to say learn bimodal distributions.
Yeah. This is a very good question. So if you apply the same logic, what you'll get. So here, like let's say that you want to like fit some samples with your density, then here you'll get EDF trading, and there you'll get square matching, which is like the basis of diffusion models. And these processes are actually, this is like tightly related to geometric averaging on the like annealing, right? In a important something, for example. And this is tightly related to diffusion. And that's why even the plot I drew like in different ways. These are, I plotted the density actually, and there you see the histogram. So I draw this in the sample space. Yeah.
So, I mean, obviously this is beautiful, but in the I would say many body physics and chemistry community, there's a lot of people that use standard codes like Casino or QMC. I forget. There's a bunch of codes that just black box codes that use parameterized trial wave functions and all that stuff. They have some energies listed, right? They say this is the energy for the system in this basis and so on. How does and for the many body people, those are the metrics that they care about. They want to see the energy and how many digits you get and so on. How well does this method do? You're showing us the traces, but ultimately like a table of the actual energies compared to other previous methods for many body physics might be useful.
Yeah, of course.
Okay.
So I have to say probably a couple of words about the baseline. So for quantum variation Monte Carlo here, this is like a relative error in the energy. And for quantum variation Monte Carlo, I just take the psi-former implementation, which is kind of the state of the art from deep lines. Maybe not really the state of the art in some tasks, but as I understood from the paper, it's quite like general. And these columns, it's the same architecture, the same hyperparameters, just a different loss function.
Okay, thank you.
Yeah.
Naive question here. So the distribution you've shown and the one that you're trying to match with yours, where do they come from?
Which distribution?
Yeah, this one, the blue ones.
Where do they come from?
Yes.
I just these are like just two Gaussians, mixture of Gaussians. It's just an example, like to illustrate how these metrics are different. Mm-hmm. So it's not the real world system.
So then, what are you optimizing in this? Like you're solving the Schrödinger equation, right?
No. Or... So here I said that so the pictures are drawn to illustrate the intuition. How are these metrics different on the space of distributions? So instead of E, you should put KL between the orange and the blue one. So this is our kind of energy. So it's not the quantum energy, it's how far we are from the target.
Okay, but what is the problem that you're solving?
Here?
Yes.
I'm solving the problem to show people how these metrics are different, like to illustrate the different behavior of these densities, how distributions behave differently when we try to minimize some functional. The functional here is the KL divergence.
Right. Sorry. Let me be more specific. Like in this whole work, it seemed to me that you were trying to get the ground state energy for chemical systems. That's the problem.
Yes. We want to solve the stationary Schrödinger equation, and this one, and we solving it by minimizing the energy.
Okay. So have you compared your approaches with any standard techniques using variational methods in classical quantum?
Yes. Right here, so the standard technique is in blue. Our techniques are in orange and blue. And this is for variance estimation because variance has to range.
Okay, thank you.
So just to follow up on this and the preceding question, in codes like Alán mentioned, the Casino or QMC pack, as far as I know, everybody's using diffusion Monte Carlo now. Is that something you can compare to? Also, qualitatively, it looks like the Wasserstein path would resemble more a diffusion kind of Monte Carlo.
So we haven't compared it directly. We follow these I know maybe this is a null-specific line of work, but we kind of were building on top of the papers that DeepMind did and some people from Microsoft Research, and we were just comparing to DeepMind's work, Cypher, which is variational approach. I'm not sure how, as I understand, the problem with diffusion Monte Carlo is in a bit different domain that you have to decide on the node surface, right? And then people, as soon as it works when people take, for example, quantum variational Monte Carlo, and then they run the diffusion to estimate the energy much more accurate. And we are not competing here with this. I think we are, because our approach is essentially just how to train these variational models in a different way that incorporates some intuition. So, yeah.
Are there any more questions? Right, if not, right now we have a 30-minute break. So let's shut up very soon. So, yeah.
Hi. All right. Welcome back, everyone. I'd also like to thank the organizers, Matthew and Luca. And I'll tell you something a little bit more from the practitioner in terms of quantum chemistry, atomistic simulation. There's a lengthy talk, so I'll have to cut it short at some point. So I don't know. Yeah, I'll be watching. This is a theme, efficiency, accuracy, scalability, and transferability, which we've been discussing in a recent review, which you will find on the archive as well. Let me explain a little bit more about this. I don't think we need to tell you much about this, but for those who haven't heard about it, there's a major effort going on here in Toronto, basically led by Alán on the acceleration of materials discovery, connecting things all the way to the experiment using robots and automation, right? And so my personal view is that what we are witnessing right now is the establishment of additional pillars of science. So if you're unfamiliar with this concept, there's this idea. At first there was the experiment, then we built that's the first pillar, then we built some theory, the second pillar, in particular quantum theory, right? And then we use computers. So the computing paradigm would be the third pillar. And now, for many years now, we've been using surrogate models on top of that, right? It's just like an onion layer we're building. That's the fourth pillar. I'm convinced there's going to be the robotic pillar coming up soon, right? So that's when the robot scientist is sort of emerging, right? I think that's when we have accomplished the fifth pillar. Now, that's sort of the hard sciences, and chemistry and materials is only one field, of course, where this applies, right? There are other fields like biology and whatnot. But so I'm biased towards this field, and there's this intriguing thing. This is our alphabet, right? The periodic table, you might remember. And the interesting thing is it's flexible, right? So in our education, there's unfortunately, for one reason or another, there's a bias in how we view things. But this is an alternative periodic table. It's not wrong. Okay, this is equally valid, or this one down here, or this one. This here, I'm not sure if it's not too esoteric, but these are also ones I like, and they are also correct, right? Particularly this one has this periodicity. It's like a damped harmonic oscillator, right? And so there's an inherent structure in matter, right? And I would argue we traditionally in the chemical sciences, experimentally, we've been exploiting this, right? This is why experiments often work so well, why chemists have this intuition and so on. And physicists always struggle with quantifying that, right? What do you mean by chemical intuition, right? And then you see that the reproducibility in the chemical sciences is actually quite low, right? So that also would indicate that you would want something more physics-based. So that's the sort of philosophy I'm pursuing. And here's just one example of what you can accomplish by rearranging the periodic table. So this was actually done in the 80s by David Pettifor, an important scientist from the University of Oxford. He proposed a reordering of the periodic table, and you follow these lines. And if you do so, you can arrange the atoms in the way shown here. And a property like the entropy of formation, which, if you were to calculate this from first principles using quantum mechanics, would be super expensive. Very, very difficult to get this right within the uncertainty of the experiment. A property like that simply becomes linear for carbides or nitrides in a given crystal structure, right? So it's basically solved, right? For that class of compounds, the problem of mapping out the compound space. This is, people continue doing this, so Hardy Gross and Miguel Marquez are well-known theoretical physicists who keep on working on this. So generally, there's this sort of landscape, and we have hierarchies of methods, right? Approximations to the electronic Schrödinger equation. Now, there are many different Schrödinger equations in the atomistic sciences, right? So for instance, you also have the nuclear Schrödinger equation, right, to describe your vibrations of molecules, of phonons and solids. However, the electronic one is typically the bottleneck, right? If you want to fully understand compound space, right, we need to understand that part for sure as well. Now, what you see here are different approximations to solving Schrödinger's equation: force field, semi-empirical methods, mean field methods such as Hartree-Fock. MP2 is perturbative electronic methods, Möller-Plössl second orders, quantum Monte Carlo, coupled clusters, single doubles. So some of these methods were mentioned already today, right? What typically happens is if you compare to the experiment, you will have errors similar to this on energy, right? Now, chemical accuracy is 1 kcal per mole. This number comes from the uncertainty in calorimetric combustion experiments, right? That's how good people are. So if you get a method that's as predictive as this, then you can skip the experiment. You can do it on a computer. Now, this notion of a digital twin, right, or that you can simulate the experiment on a computer, this is so well established in engineering, let's say. People don't even talk about it anymore. However, in the atomistic sciences, we are not there yet, right? In some sense, we still have the experimentalists doing the trial and error, and there's no prediction or very little prediction of the outcome to help assist with the experimental planning. Now, you can see the importance of improving on these methods for tight binding. DFT is incredibly popular, very accurate, often better than Hartree-Fock. Or then the functional theory, right? Basically pulling down this Pareto form, the trade-off between cost and accuracy, right? And that, together with John Popel, who also worked in this direction, was awarded a Nobel Prize in '98. Now, in our group, we try to tackle this problem of compound space from two sides. One is a perturbation-based approach, where we interpolate in chemical compound space. And so, from my view, the paper Alán mentioned this morning, right, is so important because it actually coarse-grains compound space to make it interpolative, right? So this is a very crucial step, right? But if you go down to the highest resolution, right, or the formal resolution of quantum mechanics, you can really interpolate Hamiltonians, right? And lambda is an interpolation parameter. And here, Alán talked about derivatives of molecules with respect to properties. This is just the inverse, right? Property with respect to change in your molecule, right? So from the quantum mechanics, right, there's very solid foundation of all of this. But how to coarse-grain this space was completely open, right, until Alán and his people tackled this in a systematic, mathematically rigorous way, right? Of course, people in the past did coarse-grain and interpolate around, but it was always heuristic and just trial and error. So anyhow, you can build these sort of Taylor expansions in chemical compound space, and that's a way to understand chemical space, right? And that's like saying, okay, you have two compounds, you solve Schrödinger's equation within one approximation of the other for one point, and then you Taylor expand around, right? But you can do also the opposite, right? The other side of the same coin. You can ask the question, okay, suppose you knew these empty symbols, what's the most likely value you should have for the black one, right? So that's the Bayesian formulation of things, right? And of course you can do that with machine learning. So for example, supervised learning here simply. So the variables that enter your Hamiltonian, like nuclear charges and coordinates, and then some observable, right, which traditionally you would get by solving your Schrödinger equation.
given sufficient pairs for training, you can now infer this, right? And the amazing promise of machine learning, and I just show one of the other fathers godfathers of machine learning, Vladimir Vapnik, is that it generalizes. Right? These surrogate models statistically will generalize as long as you're doing interpolation. So to put things more dramatically, right? So that's what we do in our research. We try to create some harmony between these seemingly different things. And because we all talk more about machine learning and vector, I thought I'd talk a little bit more also about the perturbation theory and trying to tell you, in some sense, what many of us are simply assuming, that chemical compound space is actually very smooth, right? So if you look at the energy, this is the electronic energy you see of a system with 14 protons and 14 electrons, okay? And they are varying the Hamiltonian and nuclear charges, which you see here, the corresponding stoichiometries, and in interatomic distances, right? So it's very much like the example Nathan gave for H2, right, where you have 2 protons and 2 electrons. And we can play this game for any number of electrons. Now, the number of electrons is just one dimension, it's one number, right? This is not what it causes the combinatorial explosion of chemical compound space. It's really about the combinations of different elements. That's what makes things complicated. And the combination of different structures, of course, right? And so you see this energy is super smooth, right? And actually for fractional nuclear charges, you can also solve Schrödinger's equation. The Hilbert space is perfectly fine with doing this, right? It's just real numbers for nuclear charges. Obviously, you can only compare to the experiment for integer charges, right? But that's very similar to the latent space as well, right? In between, you're moving in regions where you have no physical correspondence, right? And you train, of course, your model to spit out only those with realistic correspondence. So here you see the electron perturbations of first, second, third, and fourth order, very smooth, right? There's no problem. Actually, I think there's a postulate in quantum mechanics which states that the wave function is non-pathological and differentiable as many times as each. And you can... Except on the, yeah, right. If the nucleus is classical now, or if it's a quantum, yes. Anyhow, so if you pile up these electron densities onto N2, you get the electron density of CO. And if you compare that density to the one you would get from an SES, right, you can play this game down to numerical precision. It becomes indistinguishable from the actual SES density, and you can push it further also to PF and so on. Now, what is interesting is that you can then, of course, also build a basis in this space. So this is a Hessian in your energy, right? So there's a more conventional Hessian in atomic coordinates. Here you have the Hessian and nuclear charges, Hessian with electrons, right? You have electrons, nuclear coordinates, and nuclear charges. These are the dimensions of chemical compound space, right? And so we can expand them in the eigenvectors of the Hessian, right, fully. And that would be a natural orthonormal basis in which you can expand chemical compound space. You see this for this example, right? It's 2D, and any system with 14 electrons can be accounted for in this way. Now, of course, you can extend this to more systems, to more atoms, right? So these are the BN-doped mutants of benzene, right? So benzene is C6, this planar aromatic system. Each carbon has a hydrogen attached to it. And if you look at the nuclear Hessian, the eigenmodes look like this. So those who studied a little bit of electronic theory, they would recognize immediately it looks like a Huckel, the Huckel orbital scheme. It actually turns out that any coupling Hamiltonian matrix, right, the eigenvectors look like this, right? So Huckel is not so special, actually. And what changes then are the eigenvalues as you change to a different Hermitian matrix. And we can now expand all these mutants in these 6 eigenvectors, right? So you see that there's a lower dimensionality very rigorously derived from physics, which machine learning then exploits, right? Then implicitly, That's what I would argue why machine learning works the way. Now, we notice here, for instance, so all of this is rather well established, but we notice something here in our work. There's actually 3 pairs of compounds which are degenerate. And if you look closer at them, right, for instance, this one here, you see nitrogen, boron, boron, nitrogen, and here boron, nitrogen, nitrogen, boron. These are 2 different compounds traditionally seen, right? But there's actually a symmetry, an anti-symmetry in the perturbing Hamiltonian. And for that reason, these 2 must be degenerate in second order theory. And this means there's a, in some sense, these 2 molecules are identical, right? So if you only care about energy, right, then you should be able to represent them by the same string, right? So Alán mentioned the Sevich string before, right? Any such string in traditional chemistry would distinguish these 2 guys, right? Meaning we fail to account for the symmetry explicitly in these representations. We could think about creating new representations, right? Improved representations that explicitly account for such symmetries, thereby reducing training data needs and making models more efficient, right? So I would argue there are symmetries like this that we haven't been exploiting yet. So we discussed this further. You can read this up. It was published in Science Advances in 21. This is not restricted to benzene in any way. This is just an example for the same thing, the same symmetry and diamond lattice. You can also derive relationships between bond energies. So, for instance, you can simply argue that the NC bond roughly should be the BC bond plus half the difference between the 2 homolytic bonds, right? So there are rules among chemical bonds, which might be the reason why chemists have developed an intuition in the first place, right? So we can try to hard code those in machine learning, but we can also try to make use of this or try to discover this. So here's another example of the symmetry idea. If you imagine 3 manganese atoms, I highlight this in the periodic table, you could perturb this to the right, that you say, okay, I have once cobalt and twice chromium, right? Same number of protons, right? But then I can also go to the other side, and then you get vanadium and 2 times iron. Now, these 2 guys have the same energy, right? So, of course, you can do this with any other atom pair. So you can use this to rank molecules. You see here the symmetry-based rank with the QM rank, right? So there are trends throughout chemical compound space that are truly based on physics, which, again, we would like to rediscover or discover first with machine learning. And here we did this for 400 million mutants of this system, and then easily sort them and so on. So right now, this is without any machine learning, right? We can deal with 400 million compounds without machine learning in a rigorous session, right? And so I would argue we want at least make use of this to improve upon this when making use of machine learning. We also found that you can describe the chemical bond between 2 atoms as a simple model between making use of the nuclear charges of the 2 atoms. So you can partition a molecule onto its electron densities, and then you can study how the energy of one atom in the bond varies as you, and that's shown here, as you vary the nuclear charge of the other. Now, that linear behavior would suggest a multiplicative answer, right? And that's what we published in this Jack's paper here, which just recently came out. And so it's a back of an envelope model, right, of a chemical bond and chemical space. The meaning of these terms is very easy, right? Very straightforward, and you can see here in comparison to DFT, it compares very well. Right? So there are also these other models like molecular orbital theory or valence bond theory, right? And valence bond theory gave rise to Pauling's expression and the introduction of electronegativity in chemistry. These are models of similar simplicity, right? And just because chemistry has shied away from physics for a long time in some sense, right? We are only now making the progress towards more additional alternative simple models, right? And again, I think these should be combined with machine learning later on. So we have trends like this in chemical compound space. You could, everything I've shown you so far was for fixed geometry, right? Just varying nuclear charges. It's like a graph, a rigid lattice, and you're playing with the coloring of the graph. But of course, in chemistry, you also change structure, right? Now, in this paper, we've shown you can actually make that prediction and then add on top a relaxation effect. It's relatively straightforward, and there's something that can be done. So we did this for a whole bunch of systems. Now, let me switch gears and come to the machine learning finally. My story in this is that in 2011, I organized a workshop at the Institute of Pure and Applied Mathematics at UCLA, which dealt with navigating chemical compound space for bio and materials design. And at the time, what basically prompted me to do this at a math institute was that we had all these image compression software and packages out there. And I was just wondering if you look at molecules, right, these could be different images, right? And people were starting to machine learn image problems. And so I was wondering, okay, if I can turn my molecule into images, I could be interpolating molecules as well, right? And so Klaus Robert Müller, who's the chair of machine learning at TU Berlin, suggested we simply make use of a Gaussian process regression. So it's this kernel-rich regression answers we use. And so every compound is a point in the high-dimensional chemical space. And we use as the representation simply the matrix connecting all atoms. This is the Coulomb matrix. So what we say is the inverse distance matrix with the nuclear charges in the denominator. And on the diagonal, we put an estimate of the energy of the free atom at scales as v to the 7/3. Now, this has a very basic correct physics, right? If all your atoms dissociate, and that limit of infinite distances, all off-diagonal elements would be 0, and the trace of this matrix would be the energy of your free atoms, right? So that was sort of a first shot, and we generated a training data afterwards called the QM9 data, which was published in 2014, and this actually now is my second most cited paper. And this was in 2014. There was just no data. The largest QM data set were maybe 100 molecules or so for testing DFT, or those were the biggest data sets, and we went to 130,000 molecules with this. Now, what we could show, and that I think was really what prompted this effort, was that the error then of your machine learning model, right, as you train on more and more examples, that error must come down, right? So we are following, in some sense, these approximations to Schrödinger equation, which you have in the physics simulation world. We are following this now with the surrogate model. And then once trained, of course, the execution, the prediction is orders of magnitude faster. So this was really, if you come from developing these models, right, every one of these hierarchies was an entire community in the quantum chemistry community, right? Or there were many chairs created, careers built on individual steps on this line, right? And so this was an obsession with models, right? I mean, do you know the difference between a fashion show and a physics conference? As this shows, right? At the fashion show, the models work. Right? And so this was really amazing, right? You could generate models without, so it's autonomous generation of models in some sense, right? So I think it's very exciting also conceptually, right? So to us, the question is always then, if we have these learning curves, how can we get away with less, right? How can we come to an accuracy where things are acceptable, but we didn't have to spend a fortune. We didn't have to produce tons of CO2. We didn't have to invest in the experimental data sets and so on. And so we've been working on representations that help you to pull these learning curves down and connecting legacy methods. So in the next talk, Heini will talk about it. How can you make use of all these individual levels of theory to minimize the data acquisition costs? Or could you even improve on the slope? So in the last 2 minutes, I'd just like to show you one example how we can improve on the slope, actually. So if you train and predict on the same distribution of molecules, right, your slope is amazingly stable. It doesn't change much. But the representation, you can change the offset in the learning curve. But the slope seems to be remarkably stable. And there's a numerical proof and arguments that the leading error term has to decay inversely with training set size, and this B has something to do with the dimensionality. So if your dimensionality between training and testing doesn't change, it should remain constant, right? So this slope here on a log-log scale is a constant. But you can actually change it by changing the dimensionality of learning. And we did this in this paper in Nature Chemistry 2020 by training locally on a lower dimensional problem and then applying it non-locally to a larger system, right? And so chemically, we went from interpolation to extrapolation. But on the machine learning side, it's still interpolation because the chemical environments are actually redundant, right? So you actually compare, it is an interpolation in the machine learning sense and extrapolation in the chemical sense. So we did this by building around each atom a training set, right? And if you want to predict such a large molecule, you build up the training set around each atom that consists of small fragments. And we call these fragments atoms and molecules, right? And not to confuse it with another method that's well known, AIM, we call it just AM, so amens. And these are fragments, it's like an extension of the periodic table where you include also second body, third body, and so on. You start including more and more of the environment. And like this, you can locally learn the environment of these atoms, and then you pile them up for your query system. So there's some analogy also to language and grammar, which we haven't fully explored yet. You can systematically identify these fragments. So for this molecule, for instance, this would be all the amens you would need. And if you train, as you increase the fragment size, your error improves. Okay? So you have a learning curve now in terms of number of these fragments and also of size of these fragments. So they are ordered by size, right? You see here the error for the energy, it comes down, right? Now this is the error just for one query, so it's a signed error. And you do that for every query, you have a different set of local environments. So you have to, it's like a k-nearest neighbor thing. You collect the nearest fragments to your query, and then you train your regressor on the fly on this. So you can see now, in comparison, this is a learning curve. If you do this for thousands of organic molecules, you see that now we need less than 100 training instances on average to make a prediction. So with less than 100 fragments, you can predict very well. And here's the comparison to, so this is the conventional learning curve with the conventional slope, and here we change the slope due to changing the dimensionality in training. Okay, you can then apply this to big molecules like Viagra or cholesterol or Taxol or whatever you wish, and you see that things improve. And with this, I'd like to jump ahead. I'm escaping here, and I should absolutely. Oh, this is the wrong. Sorry, this is not my computer. I have to thank the people who did the work. Yeah, so you see big one is up here. He did the amen work. You have Heini here and many others in the lab who contributed to this. I'd like to thank you for your attention. Happy to.
Yeah, I have a question regarding this perturbations that you've shown before, like that. I guess the situation was that the degeneracy that was not lifted by applying the perturbation in this boron nitride system. So I was kind of curious because I understand that the symmetries were similar. Well, they are the same probably, right? So irreducible representations of that point group are the same for left compound, right compound, but still perturbation operators are different. And I would expect...
Just in sign, it's anti-symmetric. Right?
Anti-symmetric, is it?
So from here to here, you're adding a proton on these two carbons, you're removing one on these two. Mm-hmm. And here you're removing two of these two and you're adding two of these.
And so your claim is that accounting for this perturbation, for different perturbations still doesn't leave degeneracy?
No, so strictly speaking, it kills the odd orders, right? And so you're exact up to second order.
Okay.
So it's not an exact symmetry, right?
Okay, thanks.
Thank you.
Okay, I remember you put in Twitter a bet. Remember, you had a bet of how many molecules you needed to get to chemical accuracy. I forget what was the bet. I remember I put
9 challenge.
I remember I put like $200 towards the winner.
You committed.
Yes, I committed $100 for whoever wins, and you too. And where are we in the QM9 challenge? Like I remember you used to show. Yeah, I mean that was a challenge of how was it learn the energies of the QM9 data set with less than 100 molecules? I forget, right?
So in QM9, we have, it's being used as a benchmark, right? And it's very interesting because many different representations have been tested. And so far, probably the best representations, they require around 1,000 molecules for reaching chemical accuracy, for reaching 1 kcalmol. The QM9 challenge is an award for the person who reaches chemical accuracy by training only on 100 of these examples. But of course, you should not be using other QM results from anywhere else, but just that data set, right? So that's sort of the inherent challenge. Can you develop a model trained on the same data set with such efficiency that it requires only 100 training instances? And there's a whole range of professors who committed $100. So certainly, I think it's 2 or 3K if you're interested.
So the award ceremony will be here in a year from now to the student here in the room that solves the problem, right?
Hello?
Yeah.
Hello, is it working? Oh, hi, Anatole. My name's Chertian. I work with Alán. So I have a question. A lot of the examples here you show are for energy, like is it predicting energy? So I was wondering how, if it's possible to generalize this to properties. So for example, graphene and graphitic boron nitride are maybe isoelectronic, but they behave very differently in terms of the material's properties. So I was wondering if this framework could be extended towards predicting properties of materials.
Yes, so thank you for clarifying this. Our approach is really physics-driven because of this, right? We know how to account for properties, right? The properties are your observers. So these are QM expectation values. And we can apply perturbation theory to them as well as machine learning, right? And we even applied it to subnet averages, right? So going back to the definitions of physics, right? It really helps you to properly set up the machine learning model and to ensure that training and prediction will work. Right? The true challenge, I think, is to actually estimate offset and slope in learning curves. Right? Usually, if you're given a new data set or a new problem, We don't even know how many training instances you would need to reach a desired accuracy. We don't know offset and slope of these learning curves. And so far, everything I've seen is purely empirical. So you need to start training on a subsample and then you estimate things.
Hi, everyone. I'm going to talk about multi-level learning and also the minimizing data acquisition costs. So can we reduce the amount of training data in our models, but maintain the accuracy, right? So we know that 10 years machine learning chemistry works for applications, but what about efficient machine learning? So why is it important? Here you can see the performance of the top 500 supercomputers in petaflops over the past 20 years. And 35% of this is chemistry and materials. That's a large amount. On the right, you see an energy forecast. So we see the energy we need will increase and also the cost, partly because of the Ukraine war or whatever, but cost increase. So I want to do my part, and I want to try to optimize or minimize the training data. So the cost by maintaining accuracy, so reducing the carbon footprint of chemistry, or in other words, just make chemistry green again. Yeah, here that's the same figure you saw in Anatole's talk. So you have the accuracy versus the cost. Here's a Pareto front of the empirical Hartree-Fock perturbation theory of the cluster. Above, you have the nuclear charges, the geometry, you solve the Schrödinger equation, you get the energy. And in machine learning, you have the same input, but instead of solving the Schrödinger equation, you train your model, do the predictions, and then you end up down here. So hopefully. Now, Peter Tussell and Bing Huang from our group, they introduced CQML, so it's multi-level learning, 4 years ago. So where you see you have Hartree-Fock training data set and the training set size as dimensions. So in this work, I just use the training set size and the level of theory. So it's basically a treatment of electron correlation. So it's Hartree-Fock MP2 couple cluster. You see on the right this telescope series here. If you rearrange to this one, it's basically this equation down here. So to get couple cluster energies, we have the Hartree-Fock. Then we calculate the difference between Hartree-Fock and MP2, and then the difference between MP2 and couple cluster. So it's important for multi-level learning to have a hierarchy. For example, this one here. This is a summary. It's not complete, but it's just a summary of different data sets. You see some empirical, DFT and couple cluster in 3 different families, and they're ordered according to the publication time. I mainly focus on this QM9 data set and the multi-level one. And also others. And here in the summary, you can see we have a lot of semi-empirical data. We have also many DFT data, which is basically a working horse in machine learning quantum chemistry. So it's basically presenting giving the data where we train our models on. But we don't have a lot of coupled cluster data. So now I use kernel-rich regression in this work. So this is the basic equation. So to do a prediction, you just loop over all your training molecules, compare it to your spheric compound using an L2 norm, a Gaussian. The regression coefficient you get with inverting the training kernel times your label. That in your representation space, the property you directly predict. It's just kernel-rich regression. And then in data learning, the difference is you have a baseline. So you calculate Hartree-Fock, and you just learn the difference between your baseline as a Hartree-Fock and coupled cluster. Only difference between those two. And the main difference between multi-level learning and delta level learning is are these two arrows here. So in multi-level learning, you also predict the baseline. So in delta level learning, if you want to make a prediction, you also need a Hartree-Fock calculation. In multi-level learning, you also predict your baseline. And now I use Bayesian optimization to optimize the training set sizes. So here on the left, you see the original work from Peter Saspel, the training set size of coupled cluster, MP2, Hartree-Fock. They have heuristic ratios 1, 4, 16, and those were also the input for our Bayesian optimization. I have two cost functions. One is just the cost. So basically, you sum over all your training compounds and you add up the time. So by the time you need to generate your training data. And the second one is this combining cost and mean absolute error. The parameter beta can be between 1 and 0. It's also normalized between 1 and 0, the cost and the mean absolute error. So we then run this one and we get better ratios out there and reduce the timing while maintaining accuracy. Yeah, and I'm using learning curves. So you saw those equations before, and basically if the orange dot is the one we want to predict, so query compound X is a training compound, you get an error. The more training points you add, the lower your error will be in optimal case. And learning curves are great, so you can compare different models, or you can estimate how many more data do you need to reach target accuracy. I have a third method to estimate the optimal distribution of training set sizes in multi-level learning. So this is basically, we take the mean cost, so you just calculate the mean timing of your training data, and you calculate a null model, and in this case, the null model is just you take your training data, calculate the mean of the properties, use this as a model, and then do the predictions, and you get an error, and the error is here ML. And you assume a slope of your learning curve of -1/2. So here you can see the code. So we have the mean timings and the null model. You basically do this is the cost. It's the same as here. And those three are the null models looping over those. And in the end, it's just error propagation. Then you loop over different training set sizes. And in the end, it's just brute force. And it gives you an estimate on how you should distribute the training data between those models. The data sets I'm using is QM7 properties, optimization energy. I also have QM9, this one with local coupled cluster and EGP. So it's work in progress, so I only have results for those three, but I will produce the others. And then here, AE stands for optimization energy, EA is the electron affinity, and IE is ionization energy. And here you just have the coupled cluster one. It's just the level of theory with better basis sets, more expensive. I also need timings, and here for the same data sets, you have the timings. You see smaller molecules. Calculations are faster, QM9 a bit more. It's local coupled cluster. If you go to coupled cluster, it gets more expensive. So I have one problem. This data set was calculated using Gaussian, and they do not allow to publish timings. So I used the work I did before. So using the same representations and kernel-rich regression, but changing the label from energy to runtime of a calculation, I was able to predict the runtime of quantum chemical calculations. Here you see the CPU error, so how long a calculation took, the predictions down to 2 seconds, and here's the relative error. So basically, I trained a model, predicted the timings, so that I have a cost for my Bayesian optimization. Now the QM7B, we use these 3 levels here. So this one, top left, is a grid scan over different training set sizes. So every blue dot is a model on different training set sizes. And then using this cost function, I just colored the dots according to the cost function. You see if it's 0, that is 0. You ignore the mean absolute error, and you only care about the CPU time. So the lowest values are here on the left. It's like CPU time versus mean absolute error. And then as you increase beta, then you also lower the slope. And if your beta is 1, then you only care about the mean absolute error and your best values are below there. For every beta, I chose the lowest cost here and marked them in orange down here. So it's basically your Pareto front. If we zoom in, you see here the Pareto front, the blue dots are the grid scan. S2, the red one is always the original work from Peter Tussle. So that's 1:4:16 ratio. That's what we want to be. And CPU, the constrained one, is one Bayesian optimization model. And then for all these betas here, I ran the Bayesian optimization as well as the guess I introduced before. And beta was also then in optimization varying. And you see we move the Pareto front here to the left, but do not reach chemical accuracy here. It's a bit because the timing of copper cluster for so small molecules are the difference not big. So, however, I still generated learning curves introduced before, direct learning, and then the red one is here. And even with the guess, the simple guess, we are better. So we move from here. That's just the largest training set size versus the mean absolute error. And on the right, you can see a Pareto front with the total CPU time of your training data versus the upper cluster training set size. So where you want to end up is in the bottom here. And the bar plots are just the ratios between upper cluster and between Hodge-Fock. So if you are on the left side, you see that you need much more Hodge-Fock calculations, but therefore fewer upper cluster. And here on the right side, you see it's more upper cluster, but fewer Hodge-Fock. So in principle, you want to be more on the left side. Here you see in the range of 4 copper cluster calculations, the slope is not as good as from the others. My guess is if you increase the number of copper cluster calculations, you will also get a better slope. However, I don't know and don't have enough data to prove it. So that's why we go with this one, for example, for the rest one. The next data set is the local copper cluster one. So it's QM9, same story again. You see we are improving, we're moving to the left, so we use fewer and fewer copper cluster training data. And again, here on the left, you see you need much more Hodge-Fock calculations than copper cluster. And the best one here is around, say, 400 to reach chemical accuracy. So these plots are always at where the model reaches chemical accuracy. And the original one is here on the right. And the next one is the copper cluster one. So the same story. We have here we only have 4,000 data points, but if you just do a fit down here and then extrapolate to 1 kcal per mole, you see that the best models down here, or you always use more Hodge-Fock, like the ratios basically 1 to 10 to 200. So this also means if you have a very good baseline, your predictions will be better or your model will perform better. And it luckily is also the cheapest method. Then there's another data set I didn't introduce before. It's from a group in Denmark. So it's DFT for QM9, and I wrote Q density function 2 because those are the functions they use to calculate energies of QM9 molecules. And now, in multi-level learning, you need a hierarchy, and in DFT, the best guess is Jacob's ladder. So I asked ChatGPT and Google Bar to group them according to Jacob's ladder, and it was just a disaster. So what's just wrong? So best case, maybe all of them were right. So I looked it up here, and then I distributed them according to Jacob's ladder. So use local density approximation, GGA, GGA, hybrids. From this hierarchy, I then just for TPSSH, so for the hybrid ones, I just calculate the differences in an old model to a couple cluster. I took this one and for all the others, I did the same and just compared it. I mean, I just need a hierarchy and I want to see how it works. And here on the learning curve on the right, you see it still works. However, I do not have timing, so they didn't publish timing. So what I have to do now is I do reference calculations, take the timings, train a model, predict the timings, then put the timings and the errors in my Bayesian optimization, and then I will get better ratios for multi-level learning. And here's just a plot of the energy distribution So basically LDA and the TPSH, and here are the deltas of those. Yeah, and as a summary, we see here that the total CPU time needed. So it's the original work, the guess, and the best performing one from the presentation. So in QMB, which is a very small data set, we save about 10 hours. That's not so impressive. Here it's about, I don't know, 800 hours. And when it gets very expensive, here on this one, you see you save about 1,800 hours in generating your training data. Next step would be, can we combine those two, basically local copper cluster as another dimension, as another level in the electron correlation, but because they have different basis sets, I also need to add the basis set as a dimension. So yeah, this was my talk. Other questions?
So I have a question regarding quality of couple cluster theory and like predicting or correcting. I guess did you try to correct couple cluster theory with your machine learning techniques, or it's just trying to reproduce it?
No, for me, couple cluster is the highest level. That's what we try to reach.
I see. Okay, thanks.
Is there any other questions? Maybe sit down once we're back again. Right now it's lunch. I think it's ready. So we'll have lunch until 1:30. And yeah, you can access right outside by the
yes and no. Some have this person, some don't. No. I mean, this is a hierarchical world, so information there should be. Now let's imagine that there are starting some entanglements. We bring them closer together. The guy on the so I am going to want to go ahead. I think that is a good challenge. I think if you have like a full density thing, what they have, I guess, so you have all the electronic coordinates, then it's probably, you can just plug it into. I think if you only have the density, like a constant three coordinates, I think it's
because you don't know where the electrons are.
Yes, you just know that there are some electrons. Okay. Where they are.
But you need to know that if you say I don't interfere. You have that to, I mean, the difficulty
yeah, but like the density matrix is it's like a huge matrix, right? This is
you can take the density function.
Reservation theory is good.
Yeah, but how do you
how do you find how do you know how often two electrons are? Yeah, that's all the current. Yeah, now I think then it will be fine. I think it's only when you thrown away all that information, integrated out, and only have one coordinate left. I think that's what you. Oh, okay. So, I think that's why. Yeah, I think that's where all like when I have the two of these two functional. I think that's where it comes from because you can do it in principle, but it's just hard to find in the ground.
Yeah, but if you had entropy, then you can use that again.
You could do what?
Like if you have n, then you just add it in. Three-dimensional value. Like finding it is hard. But you have n information. Yeah, actually, if you have expression.
I think some of the subtlety, at least what I could see, was that if you have n, there's not a one-to-one correspondence to the actual wave function, unless you also know the potential. Like if you only know the density has two peaks, you don't know if the electrons are both sort of a bit in both, and are interacting a lot, or if they're in separate spaces and don't interact at all. So, and then evaluating. Not sure.
Yeah, this would be right. And then you can go
one of the methods seems to be the exact thing that seems to be what I found at least was to once given the density, you minimize the energy over all wave functions with that density, and then you have the wave function. Super expensive.
Because I guess that it's from now because the next area works. I guess you confirm the
I think that corresponds to this minimization, but where it's not over all possible size, but just over non-interacting.
Yeah, one thing. I think because if you trace everything else except one, then you have a lot of information about how they interact.
Yeah.
So if you have
I can show next time a better indicator.
what is then there? They made a really clever argument that in principle go from density to external potential. So it exists in principle, but no one knows the form solution.
So we find that you have an expression for there. You have an expression for the understand sure about actually hard to
Yes, with
so it seems that I think that in parallel, I think the more high level approach. We're not focusing that much anymore.
I can't.
Electronic chargers. And it seems that our
search for specific
money technologies like this are kind of very that when So one advantage of this UI on reaction. On people. Reaction to my future there's got to be like you got to achieve no one can do it money. No one can do it. Yeah, that is how it works. My money and why? 8 hours you can always prove that. We can look like I think I might well, one thing that they wanted how long does this roaming take? I was planning to do it.
It's the fact that it would be possible, sort of surprising.
That's what we
Going from density to energy. I mean, that must be some property of the machine.
how do you mean going from
Thinking to energy. Density throws away a lot of time structure.
But yeah, you need like expression of kinetic energy. Mental energy.
Oh yeah. Yeah.
And room there.
Oh yeah, yeah. Even if you have the ground state density, that's an arbitrary density, arbitrary energy.
I think the formalism supports that if you have to count the density, you should have to count the energy. And would you obligate for? Would they be, yeah, I mean.
That's a minimum requirement.
Yeah.
I would like to also be guaranteed that to have an arbitrary density. I could use the principle of these methods.
Yes.
Energy of it. Energy can.
I guess it's just whether you operate in a weight function or you operate in density, right? To get to capture energy.
So much of a smaller object.
It is strange. Yeah, but the whole idea of the functional operates directly on the density, right? If you don't see density, well, I guess thinking of it as functional because density is a function of electronic force, right? And then the energy is something that operates in the density, is something that operates on the electronic coordinates. So if you remove the fact that it's dependent on electronic coordinates and then you just have the density, then I guess then it's not really a function, it's a density function. Yeah. The density functional means the density itself depends on the density itself is a function. Yeah. Yes. Yes. Density is a unit. Probability to have it. Yeah. So
One over.
Or something like that. The electrons per state. Yeah, the 1 over volume. Right? What do you mean? Submitted?
This one. Oh, amazing. Like that it's about Bacon storage code. It's written by Bacon. The title is just Bacon code. And if you scroll down to share the contribution section, Bacon attempted to write code, completely wrote code, and insisted on
Get it married there. Really coming to SCF, right?
Yeah.
You're wrong, I'm right.
So I'm guessing there we could have like
his email to Gmail. Yeah. That's a weird flex. No, I mean, yes, but also, like, I thought they have Google. Google.
Oh.
Yeah. They don't have Google.com.
Yeah.
You know. The Microsoft employee having
That's 420 hotmail.
I still don't see how actually have cannot be that hard.
No. I mean, no, it's the function. Literally, you just use the function. You put it into the function. Yeah, exactly. There's a, sorry, what? It's a f of rho, right? So you just put the rho.
Oh, yeah, the potential, yes. But what about T and electron?
I think the T is a little funky, right? I think the T of density function theory is a little funky. I remember.
Where's the function?
Yeah. It's just like some uniform electron gas, some shit like that.
Yeah, so and then all the like Git code, so like Wednesday, probably still working with. I guess tomorrow. My plan was to like write up what you know.
I don't know if you complete that.
Yeah. I didn't make it. Yeah.
I don't know.
Yeah. When we get the variation of the total density, I don't know if that doesn't seem like an exact thing. Maybe to do the question.
Yeah. Yeah. I think it's like a first step, maybe just being variance as a function of the orbital, like ignoring the everything. So it would be like 0 if you include all the spin orbitals. Remove one. Of like the ground state, like the FDR. Yeah, so like if you use like the cap orbitals, you have to solve for the variance. If you said it would probably be small. We said like a first step.
There's the kinetic energy functional and it's known exactly. Or yeah, I don't know. I wonder if it comes from you assume that there's a non-interacting, like a system full of non-interacting particles, there's zero potential, and then you have the looks like it's you get that T from there, and then when it starts interacting, then you have
it's always interaction.
Yeah, the interaction is puppy. I guess the exchange correlation functional also has a kinetic part.
Yeah.
Exchange correlation?
Yeah, like it should have a kinetic part to it. In addition to
remember the error in some of it is for kinetic energy.
It should be.
It is tiny compared to the error in potential.
Yeah,
that's where people.
Yeah.
Probably if you have high quality, then
the extra computational cost for limited accuracy analysis. Unless it's something you get for free, which I don't think it is. Might have to do with the software.
Do like a interaction with like a new CLG.
And you just do the partial trace with everything else. That's feasible. And it probably can't be that much money. I mean, that's
You get.
And you have probably
like you're starting from a where would this is the yield? Like it would relate n and rho.
yeah, no, I just run translate everything.
Yeah. Yeah.
And I want to and just about this, I don't know what they presented was like this.
Yeah.
And then if you have to see like
So then, and just So then it was.
Or maybe they actually didn't have it. Oh no, they have it.
I think it was because they could do the
gradient.
Yeah. Like they had an expression with like a tangent log Q base value as well. I think it's because they actually didn't trace that all. And Q was actually norm. Then I think
then it's, but I think it would have which dimension is like? It's 3 dimensions.
You don't have a pointer.
Yeah.
Yeah.
Not for you.
Yeah. From the cheap example of not knowing whether the one electron needs or not, they're both. I'm sort of confused as to why.
But what you can do with
if you have two electrons that are strongly interacting, then them being one in each well and them being both in both wells should have different energies because they interact when they're close. If you
like this, right?
yeah, like
that's a weak question, or
like if you put a cat here and a cat here, that is that should have a low energy. But if you put both cats here at the time both cats here at the time, I would expect that to sound very different. Higher energy. But they have similar.
But if the cats are identical, if they're both identical, right?
Yeah.
What's the difference?
Yeah.
So, okay, so
the extent of the cat.
In the sense of potential. If you add the two potential that corresponds to this and this case, then they will be the same, right? You have one potential that says the cat is a little bit here, and then there's the other potential. Like the cat is on them, you get it.
I think yeah, maybe I'm inspired by the way I found that you did it was by you have to do a minimization.
Right.
Hello, everyone. My name is Diana. I'm in ChemSpace Lab with Anatole, and today I'm going to talk to you about Hammett regression for predicting the activity of homogeneous catalysts. So throughout this presentation, I'm going to use one specific homogeneous reaction as an example, the Suzuki-Miura CC cross-coupling reaction. And then I am going to predict the binding energies of one of the steps in that reaction using Hammett by fitting two very simple parameters. And after that, I'm going to predict the binding energies of all the steps in order to make a volcano plot. So what we want from a volcano plot is usually just to tell us how, which catalysts are the best from the ones in our data set. So why are catalysts important? So what they do is they decrease the amount of energy that you would need to make your reaction happen. And in today's industry, 85% of all chemical processes use catalysts. Their domain ranges from like pharmaceuticals, oil refining, plastics manufacturing, and food production. And one very good example here on the right is Haber-Bosch, which is for the production of ammonia. Ammonia is a fertilizer that is responsible for up to 60% of global food production. And this reaction consumes 1.2% of global energy. It used to be a lot more, but thanks to advances in research, including catalysis research, it comes down to 1.2, but it's still high. At the same time, the hydrogen that we use in this reaction comes from fossil fuels, up to 90% of the hydrogen. And we all know too well that it's bad for the environment, it's a non-renewable energy, and as such, this reaction is responsible for 1.2% of the global CO2 emissions. Also, 90% of the costs are relative to fossil fuels. So in the catalyst processes, the most popular is heterogeneous catalysis. We talk about heterogeneous catalysis when the reactants, products, and catalysts are not in the same phase. Usually the catalyst is a solid, and the reactant and the product would be in the gas or in the liquid phase. Homogeneous catalysis is the case where all the reactants, products, and catalysts are all in the same phase, so all gas or all liquid. And it's very popular, but Hammett hasn't been used to predict the binding energies for homogeneous reactions yet. So as I said before, most the natural gas prices affect the price of ammonia largely. And we already know that natural gas prices are very sensitive to a lot of factors, such as the Ukraine war, which was a starting point to a huge spike in prices. At the same time, this war made the price of metal catalysts soar. And those metal catalysts are already precious and pricey metals to begin with, so mostly ruthenium-based, platinum-based, palladium-based, very expensive. So all of those are just arguments as to why we need to find new catalysts and fast. However, trial and error, that is a principle that is used in experiments, is slow and it's taking years, which is why we need to accelerate the search, scan through all catalyst space in order with predictive models in order to make it more efficient. So that's why we are proposing Hammett equation to explore that catalyst space. The Hammett equation is a very simple linear model for free energy described by this equation here, where K would be your reaction rate or an equilibrium constant of a reaction that you're interested in, and K0 would be that of a reference reaction. And Hammett developed this originally for benzene derivatives. I've circled one example here, where rho would depend only on the reaction that this benzene derivative would take would participate in, and sigma would be dependent on the substituents only. So by substituents, I mean like the ramifications that are attached to this main ring here. And our idea is to use the same concept, but for homogeneous catalysts. Homogeneous catalysts usually look like this, where you have a central metal, and then you have a bunch of ligands attached to it, surrounding it. So our rho would be specific to a type of metal, and sigma would be specific, would depend on only the ligands. The ligands don't have to be the same, so the combination of ligands, basically. And we're going to, and that's equivalent to the binding energy, which is basically the difference in energy between the state where the metal and the ligands are all bonded together, and the state where the metal and the ligands are separate. So it's a difference in energy. So our goal is to predict those binding energies and then use those binding energies to make volcano plots. And this is the reaction cycle of the Suzuki-Miura reaction. It has 3 steps: oxidative addition, transmetallation, and reductive elimination. This is how the catalyst is going to look like. So we'll have a central metal and 2 ligands attached to it. The method that we're going to use to make the volcano plot, while volcano plots were originally mostly used for heterogeneous catalysis, but another group here found a way to use them for homogeneous catalysis. And the way you do it is by predicting the binding energies of all the steps. So here I have like a conceptual thing that shows the method. So say you have certain reactions that have these many steps. You'll plot all of the binding energies of all the steps versus one reference step. And what you'll get, they'll cross themselves in this way, and you'll just take the minimum of each region. That will lead you to get a volcano-shaped plot, and that will give you the information as to where the ideal catalyst would sit. So what you want is that are the catalysts that would sit on top of the volcano are the ones that are ideal, basically, because you wouldn't want a binding energy that's too strong, meaning that it's going to be on the left side, or that's too weak on the right side. Because if that's the case, then your reaction won't start at all, or it will start and then will be stuck in one intermediate step. So that's the method. And we'll move on to data set 1. I'll have 2 data sets in this project here. So data set 1 has 25K energies of just the oxidative addition step. There are 91 ligands in them, so about 4K L1L2 combinations. Those ligands belong to 4 types: pyridines, phosphines, NHCs, and other minor groups. We'll have 6 metals, so all transition metals belonging to the period group 10 and 11 from the periodic table. 7K of those energies came from DFT calculations, B3LIP, and 18K came from machine learning calculations. We kind of have 2 duplicates of data set 1. So the first one is a mixture of the 7K DFT plus 18K calculated with machine learning using Bob as a representation. Bob is a representation that a molecular representation. I think Anatole touched on it a little bit before, and I'm going to explain it also more later. And Slatum is another molecular representation. So 2 duplicates, basically. I also have the distributions of the types of ligand pairs and the metals. And what we can say at first glance is that the metals dictate more the range of the binding, where the binding energy would fall, more than the ligand combinations will. So moving on to the parameter fitting, I'm using a code that was built by a colleague in our group, Marco Bragato. how it works is that we first set E0, which is a median of a subset of the sample where all the metals are always the same. We do this for numerical stability. Then we initialize rho with Hilsen regression. A better way to visualize this is to make a Hammett matrix where each column would be associated to one metal and each row would be associated to one ligand combination. So one row parameter per column and one sigma per row. The numbers here don't matter too much. The size doesn't matter too much. It's just for explanation. So what we can say is that the row of metal 2 relative to metal 1 would just be the regression coefficient between those two columns. So that's what we're calculating for any two pairs of metal, 1, 2, 1, 3, 1, 4, and then 2, 3, 2, 4, and so on. At the end of the day, we're going to have a matrix of slopes with 6 columns, and we just solve that for row. And to avoid trivial solutions, we just put one of the rows as 1 as a reference. We move on to calculate the sigmas, which is simple enough because it's just each binding energy divided by rho. And then we can refine rho with minimization problem using least squares. So here you have your prediction, rho times sigma plus your E0, the reference, and here you have the true value. After refining rho, you can do the predictions same as before, rho times sigma plus E0. So here are the results. After fitting the parameter, we can make a Hammett plot like this. I've used free metals in this plot just so that it's easier for us to see. The scatters are the true energies, and the lines are the Hammett fit. So the slope here are the rows, and I plotted them against sigma. And overall, the result is 3.8 kcal per mole on the fit on the full data set with 25K points. But we see a further improvement when we train on the subsets of ligand pairs, even though those subsets are a lot smaller than 25K because we have like 10 different types of ligand pairs in our data set. So that's remarkable. Also, given even the 3.8 is remarkable, given that the energies range from -100 to 100 kcal per mole. Also, what we've noticed is that most of the outliers are silver-based, and the silver-based complexes are usually overestimated. So we moved on to compare our results to a well-known machine learning model, kernel ridge regression with Laplacian kernel using learning curves. So maybe you're a little bit more familiar with learning curves now after Heine's presentation. And we tried different representations. The first one is the Coulomb matrix, which is pairwise Coulomb potential between all the atoms in a molecule. So that's one way of representing a molecule. Another way is bag of bonds, which works by binding all the types of bonds in a molecule. The third one is MDDF, which uses many-body distribution functionals. And the fourth one is SLATM, which uses 2 and 3 body terms. The two body terms is London potential, and the 3 body term is the Axelrod Taylor-Muto potential. So remember at first when I said 7K are from DFT? So we used those representations to train on the DFT data, and we noticed that SLATM and Bob work best. That's why we used Flatem and Bob to predict 18K out of sample data, and that's how we reached 25K training points for Hamet. So these are the learning curves for Hamet. The one on top here is what's trained on the DFT plus Flatem generated data, and the one below is from DFT and Bob. And after that, we did delta machine learning. So delta machine learning just works following this equation here, where you basically learn the error that was associated with Hamet so that it can become a correction factor afterwards. And the difference in performance between the Flatem-based and Bob-based data sets are even more pronounced, and the lowest is 1.6, around 1.6 kcal per mole for the DFT plus Bob data set. So now we move on to a second data set. I decided to use this because we need the energies of all three steps in order to make a volcano plot. And unfortunately, the first data set didn't provide all those the energies of all those three steps. This one is smaller, 291 energies, but it has energies for all three steps, so 95 per reaction step, all from DFT. Same metals as before, and 17 ligands. So this is a volcano plot that we got. What you see, the region between those two vertical dashed lines is where ideal catalysts would fall according to literature. And according to our Hamet plus delta machine learning prediction, the region would be larger, but it still overlaps, so that's good. And these are the results. So the MAE is maximum 6.81 kcal per mole after Hamet fit, and it reduces to a maximum of 5.74 kcal per mole after delta machine learning, which is very impressive given that we only have 40 points in the training. So if we consider this region that's given by literature, we have 6 complexes that are ideal, and I've ranked them by price here. The best are palladium and platinum, well, mostly palladium, which is an agreement with literature. So 5 of them are palladium, and this one here is platinum. However, if we take a look at the regions that our Hamet plus delta machine learning predicts, then we would also have this one here and this one here that are nickel-based, that are like right at the border. So at first I was tempted to think that nickel would be better in terms of price because it costs 100 times less than palladium. But then I noticed that there is a ligand metal price trade-off because since nickel is less performant, it would need ligands that are pricier in order to work. So at the end of the day, the best catalyst from our prediction is still palladium-based, and the price is $5.74 US per millimole. So that's what Hamet gives us. It works for metal organic catalysis with absolute error of 4 kcal per mole. Furthermore, delta machine learning improves this by reducing it to 1.6 kcal per mole for a training set of 20K. And it's useful for volcano plots to identify optimal ligand metal combinations and explore the catalyst space. And that's what I have for you today. Thank you for listening, and let me know if you have any questions.
So you mentioned outliers, silver compounds in the plot. So could you comment on why are they usually outliers? Where exactly, or what part is not capturing the structure properly? Is it the electronic structure, or is it fitting, or it's maybe hammered what?
Yeah, that was actually part of the work that I'm planning to do next, because as you saw, the Hammett equation is very intuitive. It's not physics-based or anything. It's just rho times sigma. So it doesn't really, it works, but it doesn't really tell us yet. It doesn't relate to the physics yet. So I guess trying to explain this, like why this relationship works with physics, is something that might be interesting.
But just follow up, the calculations that are done on this for these compounds, do you have an idea how accurate the electronic structure is predicted?
Sorry?
The calculations that are done for these compounds, how accurate the, I guess, underlying methods are?
Like
the silver compounds.
You mean the error on the energy?
Yes.
Yeah, I've checked. I haven't checked the silver particular, but yeah, I guess that's something that I will definitely have to check when I go in that direction. But all I know so far is that the 18K Bob data will have an error of around 2.8 compared to VFT.
Okay, thank you.
Thanks for a great talk. Sorry, yeah. So when people, just a general question about catalysis design, whether or not like, you know, when people talk about catalysis design, there's I think in industry, there's big problems. As you noted multiple times, they're very expensive and they're difficult to design for various applications. And so when people talk about building and developing better and better catalysts, is this the kind of thing that they're doing? Because you talk about catalyst space, so metal ligand combinations, or are there other things that people are doing out there as well when it comes to catalysis design that also might involve sort of beautiful machine learning models like this? Or is it primarily kind of stuff like what you're doing here, exploring catalysis space through these metal ligand combinations and sort of going from there?
So in terms of, well, in the past, it has been just a lot of intuition and just trying out metals and ligands experimentally. And then recently, we started developing machine learning models. There are definitely a lot of groups that work in that direction with machine learning. But in terms of Hammett in particular, it's the first time that I'm trying it with homogeneous catalysis. The other colleague in our group is trying it for heterogeneous catalysis. And I think what's the best thing with Hammett is that it's so simple and computationally inexpensive compared to like if you would do machine learning, especially for heterogeneous catalysis. You have to do a lot of calculations to find the relaxed state, and that costs a lot of time, a lot of resources. Yeah. Yeah, sorry. Yeah.
Yeah, thanks everyone. Yeah, so today I'm going to be talking about work that I've been doing with advisor Juan and my other advisor, Raymond Laflamme at the Institute for Quantum Computing. We've been trying to understand a bit more about the optimization and classical simulation of these, what we call these parameterized quantum systems, or kind of various variational quantum onsets. And specifically, we're trying to see the effect of kind of adding in a lot of kind of constraints related to experimental feasibility, and specifically a lot of effects with noise and how that really affects our ability to optimize these systems to do some useful tasks. So I'll explain kind of what these tasks are and a bit about these systems to start with. So there are all these various quantum hardware and various experiments that exist, and they all really consist of some sets of particles, maybe n of these particles. And maybe they're coupled in some way. So maybe we also have some control over some external fields we could apply as part of some kind of optimal control problem. And hopefully we'll vary these fields over time to evolve our system to do something useful, like maybe we're trying to compile some unitary operation or prepare some certain quantum state. So we're trying to optimize these parameters, and these parameters may be very constrained in various ways. So we may have these kind of D-level systems, maybe these qubits where we only have 2 possible states for each of our qubits, and the state obviously has to be normalized. And kind of in the simplest case, we're really just evolving our system with these parameterized unitary operations. So our operator will evolve for some time with this unitary operator u theta, and maybe just a longer time t prime. And kind of some basic operations that we could apply to these D-level systems. Maybe we're just adding a phase with this Z operation, or kind of shifting or flipping our bits with the X rotation, or maybe some kind of combination of a bit flip and a phase, something like this Y operation. So unitaries will consist of these kind of basic Pauli operators, and we'll see and if we can vary these parameters in such a way that the output of these parameterized systems is something useful. So our dynamics, like I said, are really just determined by these unitary evolutions, and kind of the most formal way of stating this would be this time-ordered operator that would be the solution to this Schrodinger equation. And obviously we have this constraint that this operator must be unitary. But to simulate things, we have to trotterize or discretize this time evolution in some way. So we'll take this complicated time-ordered operator and really just split it into these discrete evolutions with a small time step with our Hamiltonians driving this evolution. And we have many choices in this Hamiltonian of what's actually driving the system, and it's based on kind of what we could implement in an experiment. So just an example here, we'll be looking at nuclear magnetic resonance, where we have these magnetic fields that are acting on some nuclei, which would be our qubits. And we have maybe control over these transverse X and Y fields over time that we can vary. Then there are these actually very weak two-body ZZ terms, and this kind of Z field depending on your reference frame. So we'll be varying these theta of time and seeing what we can do. So what we're actually trying to do is maybe we're trying to implement some specific unitary operator as part of a quantum algorithm, or maybe we're trying to prepare a certain state psi. And we can assess kind of our ability to do this optimization with these infidelity metrics. And there are various metrics you can use. Maybe if you're just looking at this compilation task, you'll just compare this kind of Hilbert-Schmidt distance to the unitary itself. Or maybe there's a similar kind of trace overlap with our state that we can use. So we want to see how these parameterized L theta infidelities are affected by various kind of aspects of these experiments. So things that we might have to include is maybe we have to bound these fields. So maybe in these NMR experiments, we have some magnetic fields that can't exceed some amplitude. Maybe we actually can only implement fields acting on all our qubits at once at each of our time steps. So we can't kind of have individual control over our qubits. Maybe we also have to have some kind of boundary conditions in time and space. And there's been a lot of work on kind of the ability to optimize these parameterized systems in very ideal settings. We want to see whether there are similar kind of phenomena and effects in these more constrained settings. But the most important effect we want to look at is the impact of noise on things. So instead of having just a straight unitary evolution, we'll have some evolution that's kind of modified by these what are called Krauss operators, which maybe would have some probability gamma, which we'll call, of there being a non-trivial operation applied and kind of creating this state that's no longer this pure kind of projective state, but now this mixed combination of states. So maybe there'll be some probability gamma there being this non-trivial, say a dephasing Z operation, or there'd be a probability 1 minus gamma of there being a trivial just no operation or no noise and a density. We want to see kind of after we've trotterized things into these discrete time steps, and also maybe trotterize this matrix exponential of our Hamiltonian into some 2 and 1 body gates, are the length of our evolution or this depth of our circuit M and this amount of noise. And this has been studied in this context, kind of the effect of noise and depth on things. We wanted to kind of see in these kind of experimentally realistic settings whether we still see these similar phenomena. And we can do that using some nice approaches from this quantum optimal control field, which really determines or really kind of tells you a bit about if you have some Hamiltonian that's driving your system, kind of what parts of your Hilbert space or which unitaries or states can you actually access. And then there are also some nice phenomena that have been observed in more kind of conventional classical learning, where we have these over-parameterization effects, where maybe if you have enough parameters or maybe a deep enough circuit in your system, you could potentially reach kind of arbitrarily good infidelities with these tasks or these target states or unitaries. So we want to see whether in these kind of noisy and constrained cases, we can still achieve those types of phenomena. So I don't need to tell anyone here about learning or optimization, but we want to see really whether this over-parameterized regime can be reached where we can kind of converge exponentially quickly in our infidelities over optimization. And you can look at things in terms of kind of this span of these generators in your Hamiltonian that dictate kind of how much of your space you can span of your unitaries or states. And then you can also maybe think about things in more of kind of a continuous time setting where if you're evolving for a certain amount of time, maybe there's some kind of speed limit or some kind of smallest amount of time you could possibly evolve your state for in order to reach a certain state. And maybe you can't evolve for faster than that because of some quantum mechanical principle that's usually related to some commutator relation. So first, we were looking just at the effect of these constraints on things. So in this case, we're looking at pretty small systems, only 4 qubits, because we actually need very deep circuits or many layers of time steps because our two-body, that's the dead term in our Hamiltonian, is very weak. So we need kind of many terms to get enough entanglement, or maybe you could think about it as enough not gates to reach kind of average good fidelities for, say, Haar random states that we're or Haar random unitaries that we're trying to prepare. So just on the left here, you could think about kind of what the trends in the infidelities over optimization just for various steps without any constraints or anything. And we get this nice exponential convergence for deeper and deeper circuits. And then when we add in these constraints, like we're bounding our fields and we're sharing them across our qubits, we can still get this nice exponential convergence. We can still reach this kind of over-parameterized regime, but we now need something that's maybe order of our system size greater number of layers of our circuit or length of our evolution time. This is really attributed to the fact that we've shared these fields across our qubits. So it kind of makes sense you need maybe n more layers to rotate things correctly to get to the right unitaries. So obviously, over-parameterization is not kind of limited by constraints, but we really want to see whether how kind of noise affects things. I'll probably skip this slide for now. This is also, we're looking at these effects known as lazy training, where maybe your parameters actually barely have to change from their initial values kind of over the course of the optimization. And you can see that for deeper circuits, you get even less change. So you're really in this is kind of another indication of this over-parameterization. And then you also can look at this Fisher information, which is kind of related to kind of how expressive your ansatz is. And you can see how the rank of that actually saturates. So I could talk about that in the discussion if people are interested. But getting back to how noise affects things, we first wanted to see just for really different amounts of noise. So there's probability gamma, if there being kind of non-trivial cross operators that give you this mixed state, how that affects kind of the best infidelities we can get on average. In this case, we're doing this state preparation task for some Haar random states. And we're acting kind of individually on each of our qubits after each of our time steps with this noise model. We see for small amounts of noise, we're really just limited by our depth of our circuit. So lighter green being these deeper circuits, we get better infidelities on average. And then as we increase our amount of noise, our kind of best infidelities we can start getting worse and worse. And as I'll explain later, we can approximate this kind of trend as being something like linearly or quadratically as a function of this amount of noise in our system. But we're trying to prepare these pure states, and this noisy channel is generating a mixed state. And we want to see whether we're actually learning something about the underlying kind of unitary dynamics that would hopefully get us close to these pure states. So we can take the parameters that we've learned in this noisy setting and just insert them back into a noiseless just unitary ansatz. So the exact same unitary operator, just without any of the mixed state Krauss operators. And we see these dashed lines here, what the infidelities we get for that, and they're actually better than the solid noisy case infidelities, which suggests we're actually learning something of the underlying unitary dynamics in this optimization. It's not just learning some kind of other mixed state that happens to be close in some other sense to these pure states we're trying to prepare. And we can actually show that this makes sense because if you look at the form of the gradients of these noisy infidelities, they're actually very similar to the form of the gradients of the noiseless infidelities. They, in your gradient descent procedure, they're really just kind of perturbably different in some way as a function of your amount of noise. But getting back to this kind of overparameterization idea, we can flip kind of what's on the legend, what's on the x-axis here, and look now as a function of depth, how our infidelities change. And we saw kind of in the just adding in constraints that we're able to get, as we increase our depth, kind of arbitrarily better infidelities, and we increase kind of exponentially better infidelities as a function of depth. But now we see for a function of amount of noise we have in our system, we're no longer kind of able to get arbitrarily good infidelities, and past some depth in our circuit, we're kind of accumulated too much noise in our system, and our optimization is no longer able to account for this noise in some sense, and we suddenly can only get worse and worse infidelities. So this noise has induced this kind of largest depth you could have in your circuit for a given amount of noise, or you can kind of get better infidelities in a sense. So we don't think this has been observed before, at least very concretely. So we were first interested whether this is really an effect of this specific dephasing model, or maybe it's something else. So first of all, we realized that as we get to very small infidelities of the order of our machine precision, we actually run into very similar trends because of numerical floating point error. So here we came up with a model for the floating point error as a function, or as kind of a description for the numerical error that's caused by just doing a series of matrix multiplications. And you could kind of model that by varying kind of the fake kind of machine precision of your computer, which would be this kind of gamma parameter in this case. And we see we again get this similar trend of for shallower circuits or less matrix multiplications, we get kind of better infidelities up until a certain point where there's been too much noise that's accumulated. And it's kind of bounded by this black curve, which would be these kind of the noiseless case. That's really only the machine precision of your actual computer. So these noise effects, so there being this accumulation of noise, seems pretty universal. It's not just specific to a certain model or not. And you can kind of see this too if we kind of can expand out the difference in these infidelities, maybe as the version that has the noise and the noiseless version, we can expand it kind of in terms of this noise parameter. And we see they have similar kind of forms between this kind of floating point model and this state preparation with the dephasing noise model, which is interesting. We finally wanted to really quantify this kind of relationship of this critical depth that seems to occur and the amount of noise in our system. So we can do these piecewise fits of these, again, these curves of fidelity versus depth. And we can kind of try and locate these locations of these critical depths. And we see that this seems a pretty clear relationship of this logarithmic dependence between this critical depth that's induced by the noise and the amount of noise in the system. And we don't think this has been observed before, this specific logarithmic relationship. So it's interesting to wonder, like, why is this the case? We've tried various methods of trying to analytically find this relationship. You could use some kind of neural tangent kernel method, or other ways of just trying to expand out explicitly these forms of these infidelities. And it's not at all obvious that there is this kind of a transition point to this kind of noisy regime where you're no longer getting better infidelities. And you can also think about things in terms of how the infidelities at optimality scale with the amount of noise. And as has been conjectured in kind of other works, we confirm that it's something like linearly or quadratic with the amount of noise. And one final observation is that we could think about things as this noise channel. There's kind of n possible errors per time step on each of your qubits, and maybe there are these m time steps. So this whole collection of possible errors could form some binomial distribution over kind of trivial or non-trivial errors imposed on each of your qubits. And inserting these relationships in suggests that these optimized systems or these parameterized channels can mitigate in some sense something like gamma log gamma number of errors in the system. And kind of beyond that depth or beyond that number of errors, the optimization routine can somehow not account for these errors. So we're interested in kind of understanding this more and why this relationship may be. Kind of ultimately, we'd want to derive these relationships analytically, especially at optimality for these infidelities. But maybe if you could do that, then you wouldn't have to do the optimization itself. And this is unlikely since these problems can be probably shown to be NP hard. But it seems like very clear, at least numerically, that this relationship and this kind of transition to this noisy regime exists. So we've shown that these overparameterization phenomena are very robust constraints on the parameters themselves. We maybe just need kind of deeper circuits in some sense to achieve this overparameterized regime. But this noise is a very different phenomena, and it really prevents arbitrary convergence up until this critical depth that we found. So it really are kind of ultimately these pretty non-trivial compromises between maybe what you could do experimentally and what you maybe want to do numerically if things converge well numerically, but it's totally infeasible experimentally. And we could look at different things. We could look at directly at these channel fidelities instead of these kind of state or unitary fidelities. We could look at things like entanglement measures, like there are all these types of measurement-induced space transitions, which is maybe a similar phenomena. This noise could be interpreted as something like that. And then you could also think about, like, what does it mean for these parameterized systems kind of without any explicit error correction or any decoding or encoding of states, how it kind of mitigates these errors in some sense. So yeah, I'm happy to talk about anything else more. Thank you.
Was it talk? No, this is we talk until we till 1:30. Yeah, I think we're like 10 minutes ahead. Okay. Sorry? People like to go at 10 minutes, right? Yeah. Yeah. Okay, maybe that's a little bit. No, I mean, yeah, it's two things, right? Like, I think Professor talk tends to be too long, and some tend to be too short. Due to pattern. Yeah, it's a pattern. I think it's not very long. No, I think it's mostly presenting a project. You can't afford to do too much detail. But then, yeah, you have so many things out there, right? Yeah. Yeah, 70 times. You cannot do that. I always cut so much content. I always cut so much content.
I was closer to the detail, so I would tend to go into the deep dive.
Right, but I guess your stuff was also very captured.
Sure, most projects are if you're actually.
But if you do it specific, you can spend a lot of time.
Yeah. As far as on hand waving.
Yeah, but also work. I was thinking that, but we'll see.
Okay. Shall we start? All right. Thank you for staying for this talk. And I'm Artur Izmailov. So I will be describing the work we do in my group, and it's mostly going to be about quantum computing rather than machine learning. And hopefully, maybe some of you will have suggestions at the end of this talk how we can use machine learning, because we're looking forward and engaging. And that's, I guess, one of the reasons I'm here today, to learn a little bit more about machine learning and opportunities. Okay, but in my group, what we're trying to do is to accelerate bringing quantum advantage, essentially, to quantum chemistry. And quantum chemistry really is about solving this electronic equation with the Schrödinger electronic equation with the Hamiltonian, which is coming from electronic structure problem. Okay, so now, because not all of you, I guess, chemists, what I wanted to do first is just to quickly introduce what quantum chemistry is, where does it come from, and to structure this talk, I'll try to kind of go for maybe 5 minutes and pause for possible questions, because I don't think I will be able to go through the entire talk, but that's okay, because 2 postdocs from my group will continue and will tell you more exciting details. But all right, so let's do this. So first, what's quantum chemistry? If we have molecules, we can write time-independent Schrödinger equation with both electrons and nuclei in them. Right, so we can write it for small and large molecules. That's the easy part. Now, how to solve it? It's hard. And well, for our advantage, electrons and nuclei are not created equal. Right, so Born and Oppenheimer figured out that it's good to separate electrons and sort of group this electronic kinetic energy and potential energies of electrons and nuclei into the separate entity, electronic Hamiltonian. And there we can freeze the nuclei as parameters, right, and formulate a different eigenvalue problem where we have a parametric dependence on the nuclei, right, so they're frozen. Okay, so even though this is now a part of the problem that we can solve easier, because now we have only electronic variables, then we still can go back and, well, from the eigenvalues, obtain these potential energy surfaces, get the energies of the full problem, right? So essentially reconstruct all the spectroscopic levels in molecules. Then we also can look at just electronic energies by themselves, because electronic energy scale is dominant in molecules, right? So you can just look at it to see how fast the reaction could be, because reactions are usually just going from A to B on this potential energies landscape. And if you want, you can also go to the multiple surfaces if, say, your chemistry is leading there. For example, this process is just a really representation of the vision. That's all in all of your eyes. This is what's happening right now. It's a retinal that is transforming from cis to trans. So we can describe that also using the potential energy surfaces. So that's why they are quite useful. And that's why in computational chemistry, this is one of the central problems. Now, okay, we separated, we froze the nuclei, and so why the problem is still difficult? Because there are still quantum variables, electronic variables to take into account. And the usual way people do it is that they introduce the single particle orbitals, and then they consider all sorts of entangled superposition of electrons kind of distributed on the single particle orbitals in the form of Slater determinants. And we'll be working in a second quantized form. So instead of just considering just 2 electrons for the hydrogen, we actually need to generally consider all possible distributions of electrons and all possible one particle orbitals, essentially. Right? So that makes our wave function exponentially big. Right, because if we encode our full wave function as like a linear combination of these products, where each n is just 0, 1, whether the spin orbit is occupied or vacant, then you have 2 to the n number of such products. That's why the problem is difficult and challenging. And that's why essentially we hope to use quantum computers to address this challenge, right? And how do we use quantum computers here? It's just because, well, it's very straightforward because our wave function occupations, each product of this kind can be mapped to the qubit product state, right? So if you have 1 or 0, and you can encode that with the qubit being up or down in this product. And using the entanglement, you can essentially get this coefficients encoded in the entangled superposition. And with n qubits, you can exactly match 2 to the n complex numbers this coefficients can be, right? So this is kind of the background material. Any questions so far? All right, so this is sort of straightforward, but if something is not clear, please ask. All right, now you probably all seen Google's quantum advantage paper, all right? So there they shown that there is a problem that quantum computers can solve better than classical. And the problem was random sampling. Now, it wasn't a very useful one. And so our idea here is to bring quantum advantage to quantum chemistry because the problem is challenging, it's nice. Now, quantum computers are not that strong yet, right? So we want to be careful and to bring the quantum advantage sooner than later. We think that we should really look for, well, systems that are in intersection of these three ovals. First, they should be high in utility. I'll explain what it is. Classically hard and quantum easy. That's the type of the systems where we believe the quantum advantage will happen first. Now, what are the high in utility? Well, simply speaking, we could focus on, within the chemical systems, we can focus on the ones that really bring some advantage to technology, whether that's catalysts that improve the processes that Diana was talking about, with the Hubbard process, for example, which takes 1 or 2% of the human energies, or organic light emitting diodes that we all use in our screens, right? So those are typical systems where we would like to speed up the process of development. Now, classically hard, we want classically hard systems because at the end of the day, we don't want to waste the quantum resources on something that can be done with DFT, which could be inaccurate, or DMRG, that could be expensive, right? So we want a classically hard systems, and something that we are developing in collaboration with Alán's group is machine learning techniques to define how classically hard the particular system is, okay? And the third part, which I'm mostly going to be focusing about, is what makes essentially any system quantum easy or quantum amenable. And the difficulty of this question is because, as in classical case, there are few algorithms that one can consider, and the different systems could be more amenable to one algorithm or another, right? So we would like to understand what makes system quantum easy. All right, so this is the outline of a few algorithms I'm going to go over, and some few tricks I will show. And as I promised in the title, it's going to be about algebra of operators. I'm probably not going to cover all of that. And here in parentheses, there are names of people in my group who made the main contributions to this topic. So the ones with asterisks, Hyun-Hoon and Ignacio, they will be talking after me, and so they will cover more these topics in details. But essentially, we are looking into variational quantum eigensolver algorithm in near terms and quantum phase estimation. And there are challenges, of course, in those algorithms. Solving those challenges allow us to understand which systems are more amenable than others. All right, so to start, just again, there is some sort of a establishment of notation. We need to deal with the electronic Hamiltonian in the second quantized form, which is the kind of the most straightforward, amenable form for further quantum treatment. And here we have creation and annihilation operators and this 1 electron, 2 electron integrals that come from classical calculations. So we're assuming that classical computer can provide us with this Hamiltonian, and that's how we see the systems, all right? And then there are like almost like 100 years ago, developed mappings between the fermionic operators and the qubit operators, which I will just define as like X, Y, Z, the Pauli operators for individual qubits, right? This is quite standard stuff. And it's exact mapping, so you get either spectral mapping between the electronic Hamiltonian and qubit one, which then becomes the linear combination of Pauli products, right? So we'll be actually working either with this form or with that form, and we can easily switch between them. So because the mapping allows us to do that. Now, the first algorithm, which many of you probably seen, and the creator of the algorithm is here, Alán, that essentially the algorithm is very simple. It's based on variational principle, which says that you cannot miss the exact ground state energy if you go with your trial functions. And the expectation values of the Hamiltonian will always be above the true ground state. And then the algorithm essentially splits the whole task onto two steps. Quantum computer prepares the wave function and does the measurement, and then it passes the result to a classical computer, which tries to suggest a new trial function and essentially evolve. And this is like a circle that goes 24/7, so you can sort of improve your wave function and eventually reach the ground state, or if you put some constraints, you can go even for the excited state. Okay. Now there are two problems here. One is I haven't told you how to actually create the state, right? And the space is pretty large, kind of within the unitary matrices or unitary operators that you can use on some simple state to create the ground state of your system. And the second problem, which I also avoided in this little cartoon, is that the measurement problem, right? So because it's easy to say we measure, but it turns out that it's not that straightforward to measure a general operator, which our Hamiltonian is. Okay, now let's talk about state preparation first. And state preparation, you can think of it like this three-step process. You can either think about preparing the unitary ansatz for the wave function in fermionic space, and then go to qubits, or you can use, if you like qubits more, you can think of the unitaries in qubit space, and then eventually you will end up with eventually you will need to present everything as a sequence of gates. So whichever part is more attractive to you, based on your previous experience, you can work in that part, and then eventually you will end up in this sort of sequence of gates kind of stage. But our group mainly works here and here in the fermionic and qubit spaces. It's just simply because hardware efficient ansatzes that some people develop in the sequence of gate area. So they very prone to barren plateaus that Nathan was talking about. So we're trying to avoid that and use our physical intuition in development of these unitaries, right? So for us, unitaries are really sequence of this, products of the exponential functions of anti-Hermitian operator with some amplitude theta. And then the natural question here is what generators should we use and in what order? All right, so this is something to answer. And here the first piece of series algebra comes into help. Because what we can do, we can present the Hamiltonian as just two parts, H0, a simple part, and we select H0 so that it's a linear combination of some operators that not necessarily commuting, but then not commuting in a particularly nice way, meaning that two non-commuting operators give a linear combination of others, right? So that is called Lie algebra in the mathematical language, and actually it turns out that you can use this kind of closure of non-commutativity in order to solve for the eigenvalues of H0. And once you solve for H0, you can use excited states of H0 to build the kind of ground state of H, right? So that's the idea. But more formally, you can always create this raising and lowering operators once you have Lie algebras. And these are the same like raising lowering operators as a harmonic oscillator, but just could be a little bit more complicated because algebras could be different than the algebras that are represented in the harmonic oscillator case. Right?
And then X is really a linear superposition of creation, raising and lowering operators that makes X anti-Hermitian. That's what we need. And there's still plenty of X's if you define them this way. And in order to make a final selection, we usually look at the gradient of energy with respect to amplitude of X, right? So that gives us very simple and nice expression, which is the expectation value of the commutator that can be estimated relatively simply using algebra to figure out which axes have a large gradient in terms of for the energy and to avoid essentially barren plateau issues. Now, we can do all that in either fermionic or qubit algebras, and they both fermionic and qubit algebras have advantages and disadvantages. For the fermionic algebra, the expression for axes are like this. It's a typical method is like unitary couple cluster theory or adapt VQE or a few others, right? And in qubit algebra, which my group mostly worked on, we call it qubit couple cluster theory, where axes are defined like essentially Pauli products multiplied by I so that they are anti-Hermitian, all right? Any questions so far? Because I feel like I forgot to maybe pause. Everything is clear? All right. Now, what are the advantages and disadvantages? So first of all, in the fermionic algebra, it's easier actually to preserve the symmetries, but there is a price you're paying in preserving the symmetries. The gate cost is usually higher. And then in the qubit algebra, it's the opposite situation. You break the symmetries at every step, essentially. Every rotation breaks the symmetry, but overall you can recover symmetry because overall the unitary is supposed to get you eigenstate of the Hamiltonian. The Hamiltonian commutes with symmetry, so the eigenstates of the Hamiltonian and the one that you're preparing, they should be more or less the same, right? So they should have the right symmetry. All right, so just to illustrate how good is formalism like qubit couple cluster theory in terms of the precious 2-qubit gate resource. Here's the number of 2-qubit gates in blue for the qubit couple cluster theory, and in red in unitary couple cluster theory. And clearly, qubit couple cluster theory has a few gates, but without error correction, probably we still can do maybe on the current computers on the lithium age. And these are the numbers to achieve also chemical accuracy. So these are the typical results. But there is another idea here which one can use, is so-called quantum-inspired methods. And what quantum-inspired methods are the methods where you get the, ideas from quantum computing and bring them back to classical computing, okay? So since we are struggling with the errors in the circuit currently because there's no error correction, we can split some of these unitary transformations that we originally thought about putting on the circuit. We split them, and some part of it will be put on the Hamiltonian, right? Because you can always present like a product of two unitaries as unitary, right? So you take the part of that unitary I was talking about and put it in Hamiltonian. So the purpose of this is to make essentially Hamiltonian eigenstate less entangled, because the original Hamiltonian has a strongly entangled eigenstate, and then you need essentially unitary on the circuit. But if you put the unitary on the Hamiltonian becomes more complicated, but the state becomes simpler, okay? So right away, you could see the problem. For general unitary, if you dress your Hamiltonian, then there's this so-called Baker-Campbell-Hausdorff expansion, which goes forever, and your Hamiltonian explodes essentially in exponential fashion. Now, the solution that we found, it's actually quite simple, again, using a simple algebra. If your generator is just I times Pauli product, then the square of your generator is -1 because of I. And what this property is called involution or involutory. And then what this allows you to do is to truncate, not really truncate with approximation, but truncate exactly the exponent, because exponential function of such operator is just two terms, and that allows essentially exact truncation of this Baker-Campbell-Hausdorff expansion and limiting the growth of the Hamiltonian every time you every time you dress the Hamiltonian. Okay. Well, you may say, well, this is just for a single Pauli product. It may not be that powerful. Turns out this trick can be generalized, and the simple idea here is that you can build more complex operators with this involution property, which is square of them is identity, by grouping Pauli products that anti-commute. And so you can check my algebra later that if you take anti-commuting Paulis with some normalized coefficients, then this allows you to essentially build the linear combinations that square to 1. And you can use them instead of X, this linear combination. They get you even lower energies sort of faster if you use such generators. All right, so we use these sort of quantum-inspired electronic structure methods to calculate this large compound that is considered to be well, kind of old and but still good organic light emitting diet. And what this table essentially presents here is that there are several methods, and we can converge to results which are quite close to the experiment in the singlet-triplet gap compared to some other techniques from DFT and MP2. All right, measurement problem. That's another issue with the quantum computing in near terms. And a simple way to think about it, it turns out that, well, 100 years ago, or more than 100 years ago now, Stern and Gerlach did this experiment with silver atoms, and they measure Z projections, essentially, of the spin, and so that there's a quantization there. And it turns out that quantum computing these days didn't go much further than that experiment. We still can measure only the Z projections of the individual qubits, right? But as you've seen, the Hamiltonian contains multiple Pauli products. Some of them contain X and Y Pauli operators, right? So it's not only Z's, not only it's not Eisenform sort of Hamiltonian, right? Now, what do we do? There is, luckily for us, there is a way to address this by putting the resolution of identities using unitaries. And what this resolution of identities do, they don't change the expectation value that we're interested in, but they can change the Hamiltonian. They can also change the wave function. But the way they change the Hamiltonian is so that we can rotate it, and the Hamiltonian now contains only the Z operators, right? Now, that's great. The only problem that it's equivalent to essentially diagonalizing Hamiltonian. And if we could do that, we would not need the VQE in the first place, okay? So what's the way out of this problem? It turns out you can use linearity of the expectation value. So you can break the Hamiltonian to parts that are easily diagonalizable or brought to the Z-only form, right? So because diagonalizing a part of the Hamiltonian is always easier than the whole thing. And that's what we do here in this partitioning schemes. We break down the Hamiltonian into parts, and then they measure the parts, essentially, with this trick of introducing extra unitaries. There are a few requirements for these extra unitaries. They need to be simple on the classical and quantum computer. On quantum, because we don't want to overload the circuit. On the classical, because we want to know what we're going to measure. And the second requirement, which mostly Hyun-Hoon will address in his talk, is how to lower the number of measurements, because one cost of this simplicity is that we are preparing a wave function which is the eigenstate of the Hamiltonian, but it's not an eigenstate of the fragment, right? And so when you measure non-eigenstate, then you get the distribution, and those distributions could be either wide or narrow. So you would like to have fragments that have a narrow distribution so that you converge to your expectation value faster. All right, so which fragments can we use? Now, the very simple idea here from quantum mechanics, you can measure things which commute, right? And so the first kind of method is you take the qubit algebra and you group Pauli products here that those that are commuting, all right? And then it turns out you can measure them by using the Clifford transformations that essentially rotate them into the Z operators. And there is a nice graphical way to think about this. If you put the Hamiltonian as a graph, where every node is the Pauli product, you connect the ones that commute, and then you're looking for fully connected subgraphs, which are called cliques. And that is relatively standard graph problem that can be solved relatively easily. Now, it turns out you can also measure things which don't commute as long as you build some operator that you know how to diagonalize. And from the electronic structure, just a normal one, we know that, well, there's an easy method to kind of use Hartree-Fock. But one can ask, okay, what is the Hamiltonian form that can be solved by Hartree-Fock method exactly? And so to introduce that form, let's first consider this one electron Hamiltonians. They are always solvable by orbital rotations, right? So these orbital rotations turn any one electron Hamiltonian linear combination of occupation numbers, and occupation numbers go to the Z operators because of the mapping, right? These are like orbital rotations essentially. And then these one electron operators, to make them two electron operators, because we want to decompose the two electron Hamiltonian, what you can do is you can put the essentially products of occupation numbers inside of this conjugation with unitaries, and you will naturally get the two electron operators that are exactly solvable by Hartree-Fock method. If I show you these two electron Hamiltonians, you won't even recognize that, oh, this is actually artificial Hamiltonian that can be solved by doing the Hartree-Fock method. But this is very useful for the measurement. And how do we find this solvable parts? We just do the fitting. And the fitting here is that if you sum a bunch of these solvable parts, and they will all have the form of the original Hamiltonian, you just try to optimize the unitary rotations and some constants inside, so that this sum will be exactly the same as the electronic Hamiltonian that you are given initially. All right? Any questions on this? Okay. So how much time do I have? 5 more minutes. Okay. All right. Then I'll quickly wrap up this this part. There is of course, motivation for fault-tolerant algorithms, because with the VQE, the most, I guess, useful thing you can do right now is quantum-inspired methods on a classical computer. And if you want to do things on a quantum computer, we need to wait essentially for the fault-tolerant or architectures for the error correction, because simply whatever kind of advantage you get by doing more operations with the size, eventually errors will catch up with you, and you start generating garbage if you don't do error correction in the near term. Also, with the bigger circuits, you can do various kind of interesting tricks that short circuits do not provide you with. All right, so quantum phase estimation, it's another quantum algorithm. There, the idea is effectively do the Fourier transformation of autocorrelation function, and believe me, you will generate the eigenspectrum, right? But the problem there is to exponentiate the Hamiltonian. That is can be done with trotterization, and it turns out that trotterization can be well, essentially using the same ideas as in the measurement problem, because in order to exponentiate something, you need to diagonalize that, right? And if you decompose the Hamiltonian into this exactly solvable parts, you can do the trotter decomposition, and it's the same idea. It's just the error is different. Luis here in the audience is an expert in this kind of decompositions, because we were optimizing the errors with him quite a lot on the chemical systems. And last but not least, linear combination of unitaries. That's post-trotter method. which use decomposition of the Hamiltonian to linear combination of unitaries. They can be used in Taylor expansion or cubitization techniques. And there the game is to reduce to one norm. So how low can you go in the sum of the absolute values of these coefficients? And there the interesting algebraic technique is that you can again group Pauli products, because original Pauli products are already providing you LCU, but you could do better in terms of one norm if you group anti-commuting Pauli products, right? As I was showing before, this linear combination of Paulis that anti-commute, they are reflections or unitaries that are Hermitian, and so you could use them in this LCU decomposition and reduce one norm. Very simple idea. Also, interestingly, anti-commutativity is similar to commutativity in a sense it's a binary relation without transitivity, so you also can use graph techniques to find this anti-commuting groups of Paulis. To summarize, quantum chemistry is a very attractive field for demonstrating quantum advantage, mainly because our ways to encode the chemical problem is relatively compact, right? And so we're currently looking for classically hard and quantum easy systems within the systems which are high in utility. Algebraic techniques, I believe, are the ones that are going to tell us what essentially methods and what systems will be easy for the methods that are coming from the quantum computing side, and optimization of errors and cost of these quantum algorithms is a great challenge. That's going to be addressed by the two next speakers, I hope. Let me acknowledge people who did the work. This is my quantum subgroup, funding, and I guess all for your attention. Thank you.
So I have a chemistry question, basic.
Sure.
So you mentioned all these problems and so on, and they're all related to computing the ground state, even when you're trying to address chemical reactions and so on. Are there problems for which you really need to account for the electronic real-time dynamics? And if yes, can you address them with variational techniques and so on, or any other techniques?
Yeah, the answer is yeah. Of course, there are problems which involve dynamics. Usually those are the problems either in photochemistry, when you excite and then you kind of getting on the slope. I guess in one of the first slides I was showing the retinal isomerization. There, naturally you get, once you get excited from here to the excited state, the slope is making the system to go down the potential energy surface. You need, if you want to predict the time scale and observables, you need to do dynamics there. In the situations like with like when you develop catalysts, the ground state is actually also pretty good target, because what catalysts do, they reduce the barrier. If you try to develop something that kind of makes the reaction